This is daily video 1, electric current. I'm Alex Easton from Flower Mound High School in Texas. And let's review electric potential difference real quick. An electric field exerts an electrical force on charged objects, and the field strength depends on the electric potential difference between 2 points in the field. So let's take a look at an example of current. Here I have a simple circuit with a battery, switch, and light bulb. It's currently set to off. And if you take a look at on the right, you see our charge carriers, the electrons, and they're kind of moving aimlessly about. Some are running into each other, some are running into the nuclei, but in general, they're kind of moving all around. With the battery disconnected from the bulb, there's no electric potential difference, so there is no current. If we were to take all these velocities here, we would see that there's no average in any real direction. When I turn on the switch and allow the battery to do work on the charges, the electric field is going to start causing all these charges on the right to start drifting in the same direction. Some drift a little bit more to the left, some drift a little bit more to the right. We got one over here that's going to the side, but in general, there's an average drift velocity in the same direction, in this case downward. And that's what's causing the current, is we have an electric potential difference that is pushing the charges across. And the way we measure it, we're not going to use distance divided by time. That's not really helpful here because all of our charges are going different directions and different rates. So instead, what we're going to use to measure the current is a flow rate. So current defined as the rate at which the charge carriers pass through a cross-sectional area of the wire. You might remember something like this from fluids. And essentially what we're saying is if you take a wire and you were to split it open, how fast would those charges be coming out if you were to try and collect them into a bucket? That's the current. So it's the amount of charge per unit of time flowing through that cross-section. You're not going to be tested on drift velocity. Just remember it's the average velocity of the charges due to the electric field. And essentially that's what's causing the current, is all of them drifting in the same direction. And the current's only going to happen as long as you have an electric potential difference. So what I tell my students is when I'm watering the flower bed or the yard or whatever it is, and I'm ready to put up the watering hose, I don't put it up right away because I live on an incline. So one side of the yard is lower than the other. And if I lay the hose out, that will allow the water to drain because of a difference in gravitational potential. And here, what we have is a difference in electric potential. That's what's allowing the charges to flow. So let's practice real quick. We need to work on some skills, and I want to make sure that you can make some claims based on the definition of current. So here I have puzzle pieces, and I got 3 different magnitudes for the current. And I want you to take a look at the charge densities and the drift velocities and figure out which ones would go with a low current, which ones would go with a high current. So this might be a good time to pause the video, think about your answers, and then jump back in because I'm about to reveal them in 3, 2, 1. So low current can be due to a slow drift velocity, so you can have charges that are moving through the cross section very slowly, or it can be due to a low charge density. So if you look at that cross section, you would have charges that are few in number. Whereas with a high current, you can have charges that are moving through the cross section very quickly, or you can have charges that are plentiful in number passing through that cross section. Right, so what you take away? Remember, current's the rate at which the charge carriers pass through a cross-sectional area of the wire, and that's going to depend on how fast they're moving and how many charges there are. You're not going to be tested on drift velocity, and the charged particles only drift as a response to an electric potential difference. So if you remember it's the amount of charge per unit of time through that cross-section, I think you'll be okay. Thank you. And this is daily video number 2 for electric current. I'm Alex Easton from Flower Mound High School in Texas, and let's review current really quick. So remember, it's the rate at which charges flow through a cross-sectional area of the wire. And I want to take a look at an example just so we can differentiate between real current and conventional current. So real current follows the flow of the electrons. And so if you'll notice, I have the positive end of the battery pointing to the left. And when I close the switch here, the electrons are going to drift to the right instead. So the electrons drift from the negative end of the battery through the light bulb to the positive end of the battery. That's the real current. The charge carriers that are moving are the electrons. Now, when I switch to the conventional current, notice it's moving the opposite direction. By convention, we follow the positive flow of charges. So if the electrons are the one moving, or the charges that are moving, how do we get a positive flow of charges? Well, if you imagine if I were to take you and plop you down onto one of those electrons, you would notice the positive charges going the opposite direction, kind of like if we were riding in a vehicle, like a bus, a car, or whatever. As you're driving by, if you're driving forward, you'll notice the trees, the signs moving backwards. So we can model that relative motion as a current. So by convention, we follow the positive flow. Just understand it's the electrons that are actually moving. So unless stated otherwise, it's the conventional current. So real current follows the flow of the negative charge carriers, that's the electrons, and that's because those are the ones that are actually moving. Conventional current follows the flow of the positive charges, which is basically the relative motion of the positive charges. Okay, let's practice making some claims. So in this scenario, the battery is pointed up, so the positive side is up, the negative side is down, and I'm asking when the switch is closed, what will be true about the current in the circuit? A, the real current will flow clockwise. B, the conventional current will flow clockwise. No current will flow, or none of these are true. So if you need to pause and think about it, now go ahead and take the time, and I'll reveal the answer in 3, 2, 1. The conventional current will flow clockwise. The electrons, or the negative charge carriers, move from the negative end of the battery to the positive end, and that would be counterclockwise. So the positive flow must go clockwise. What should we take away from this video? Real current follows the flow of the negative charge carriers, the electrons, and by convention, the current is modeled as the flow of the positive charges. So any circuit diagrams you see are going to be using conventional current unless otherwise stated. Thank you. This is daily video 1 for simple circuits. I'm Alex Easton from Flower Mound High School in Texas, and let's review current really quick. Remember, it's the rate at which charge carriers pass through a cross-sectional area of the wire, but it's only going to happen so long as there's an electric potential difference to cause them to kind of drift in the same direction. So let's take a look at an example of a closed loop or a closed path. A closed path is any loop here that will allow charges to flow. We need two things for that to happen. First, we need a potential difference, which is going to be provided by the battery here. A lot of students think the job of the battery is to provide charge, and that's not really true. If the charge carriers are electrons, those are already in the battery, they're already in the switch, they're already in the wires, they're already in the bulb. The battery doesn't need to provide charge. Its job is to provide a potential difference. It's going to do work. It's going to push the charges through. So that's the first thing we need, electric potential difference. The second thing we need is a conductive loop. And in this case, we have one because it's all wires, or we have a filament in the bulb. So that's a closed path. Let me show you an example of an open pathway. So this open loop here is very similar. We just made one change. All I did was open the switch. So we have an electric potential difference from the battery, but that voltage is not high enough to push the charges through the open switch. The air is not as conductive as the wire, and so this is considered an open path because we don't have a conductive loop. We would need a much stronger battery in order to make this a closed loop to push the charges through the air. So just a quick review. Closed circuits are loops through which charge carriers may flow. You need a potential difference, and the loop needs to be made of conductive material. An open circuit, though, is going to be a loop through which the charge carriers are unable to flow. So let's practice making some claims based on our definitions here for open and closed loops. So here I have a simple circuit. I've got a battery, I've got a switch and a bulb, and then I've got wires to connect everything. Right now I'm going to leave it open, and before I put the ammeter in, I want you to be able to tell me what the voltmeter should read across the switch and what current should be going into the switch. So go ahead, pause the video, take as much time as you need to think it over, and then I'll reveal the answer shortly. Let's put the ammeter in, move that battery back. So we see no current. Again, the charges aren't going to flow. There's not enough of a potential difference to push the charges across the air. Now let's take a look at the voltage, because I think you'll find this surprising. If I place the voltmeter in parallel, you'll see the voltage is reading as 9 volts. Well, if I take a look at the battery, we get 9 volts here. And you might have thought, well, there shouldn't be a potential difference because the whole thing is open. Well, this whole side over here is connected to the low end of the battery, and the side here is connected to the high end of the battery. So we still have an electric potential difference. We just don't get any current because the air is offering too much resistance. So on an open circuit, we can still have a potential difference without a current. All right, and I'm going to go ahead and close the switch. And what I want you to do now is predict what the current should read and what the voltage should read. Do you think the current's going to be 0 or non-zero? Do you think the voltage is going to be 0 or non-zero? So I'm going to let you think about that. You can go ahead and pause the video if you need more time. So we actually have a non-zero current. Now that the switch is closed, we have our conductive loop to go with our potential difference, and the current can actually flow. But you'll notice the voltage has now dropped to 0. That's because if we take a look at the battery over here, the battery is using up all the energy, or sorry, the light bulb here is using all the energy provided by the battery, and so the potential difference of this 9 volts is a drop in voltage. So if I were to take this black lead here and kind of move it around, so we see from the battery we're gaining 9 volts. We're still at 9 volts. The wire is not causing a loss. And then once we cross the light bulb here, we've lost that voltage. So when the switch is closed, across the switch, there's no potential difference. It's acting just like a wire, and there is a current. Okay, what should we take away from all this? An electric circuit is a closed path, so it's a closed loop through which the charges can actually flow. An open circuit, however, may lack the necessary pieces like a potential difference, or it may lack conductive material to allow the charges to flow. All right, thank you. This is daily video number 2 for simple circuits. I'm Alex Easton. I teach at Flower Mountain High School in Texas. And let's review real quick. Electric charge carriers move in a circuit as a response to an electric potential difference. To have a current, we have to have an electric potential difference. So let's take a look at some examples of circuit diagrams, or rather the symbols we're going to use. So we're going to start with the battery. It's alternating parallel lines of different sizes. And then the bulb is going to be a circle with a filament. The switch is going to look like a broken wire, and so it's always represented in its off position. A capacitor is going to be 2 parallel lines of the same size. Your resistor is going to look kind of like a zigzag here. And if we want to show that it's variable, kind of like a dimmer switch, or maybe like the dial on your stovetop, that's going to have an arrow through it to show that it is variable. And what we mean by that is as you move the dimmer switch up or down, or dial in a different setting, what you're doing is you're moving the two connections. So it may, on the brightest setting, the connections may be so close to each other that you're not really going through the resistor. And then as you dim your light, you're moving the second connection further along the resistor, so the charges have to flow through more of the resistor. And then we have the ammeter, which is going to be a circle with a capital A, and then the voltmeter, which is a circle with a capital V. In class, you may be using multimeters, which have an ammeter and a voltmeter setting. We don't have a symbol for that because we're typically going to dial in only one setting at a time, so you just need either the ammeter or the voltmeter in the diagram. So here I have some puzzle pieces, and I have the diagram symbols on top and some more realistic looking pictures. And I want you to match the symbol to the picture. So one's a battery, one's a capacitor, and one's a switch. I'm going to give you a moment to figure all that out, and I'll reveal the answer in about 3, 2, 1. So again, the battery is going to be parallel lines of alternating size. That just represents having multiple cells. The switch is going to look like an open or a broken circuit or a broken wire, and the capacitor is 2 parallel lines. And then one more time. So again, you're going to match the symbols to like their physical counterparts. Have a resistor, a bulb, and a voltmeter. And if you need to pause the video to think it over, go ahead. I'm going to reveal the answer in 3, 2, 1. So the resistor, again, is a zigzag. The voltmeter is going to be a circle with a capital V, and the bulb will be a circle with a filament. I do want to go back to the resistor, though. Your resistors are not always going to look like that, especially with the color coding. The color code is there to designate how much resistance they're offering. So the colors may vary. You may see purple or red or other colors there. That's just to denote more or less resistance. Okay, so let's practice drawing some circuit diagrams. I'm going to give you a representation in like a FET sim, and you're going to draw the diagram for me. So how do we represent the circuit on the right using the diagram symbols we've learned? Here I have a battery, then there's some wire, a switch, a bulb, an ammeter, and then the wire bringing it back to the battery. So go ahead and pause if you need more time, but I'm going to reveal the answer in 3, 2, 1. So if you take a look at mine, notice the pieces aren't necessarily in the same spot. Like I didn't even draw it to scale with my circuit, but everything's in the correct relative position. So I still have the battery leading to the switch at the top. The switch leads to the bulb, and the bulb leads to the ammeter, which leads back to the battery. That's perfectly okay. Notice mine's rotated about 90 degrees. It's not going to matter. We're just drawing the diagram so we can make claims later. So that's what we're working on here, is just drawing physical representations. And in this case, we're using our symbols to do so. For the second one, I have a battery leading to a resistor. Ignore the voltmeter for now. That resistor is going to lead to a switch, and that switch is going to lead back to the battery. So just looking at that loop, we have battery to resistor to switch back to battery. So what's it going to look like on a diagram? We need to be able to draw these diagrams so we can actually analyze these circuits. All right. So ignore the voltmeter for now. You can cover that up if you want. But take a look. We have the battery leading straight to the resistor, and then the resistor leads to the switch, and the switch leads back to the battery. So that's our loop. And then the voltmeter is in parallel with the resistor. The two leads are on either side of the resistor. So that's how we would draw this circuit. Again, it doesn't have to be to scale. Notice in the picture, the resistor is on top. I have it over to the right a bit. It kind of depends on how much space you have on your paper or whatever you're working with. So hopefully we learned how to draw circuit diagrams. That's the big thing I want you to be able to take away is we have some common symbols that we can use to communicate with each other through these like actual diagrams, these schematics. So here's a list of them again: the voltmeter, the ammeter. Remember, for the resistor, it's a zigzag here on the variable resistor. I've just drawn an arrow, so like a diagonal arrow through it. We have a switch, the battery and capacitor. Those are different. So remember, the capacitor is two parallel lines of the same size, whereas the battery is alternating sizes. Then we have another bulb just for review, and that's all I have for you. Thank you.
Hello, welcome to AP Daily for AP Physics 2. This is topic 11.3, resistance, resistivity, and Ohm's law. And in this video, we will define resistance and explore how the resistance of a circuit component is determined by its resistivity. Hello, I'm Mr. Blazo. I'm coming to you here from Fayetteville, North Carolina, and I serve at Terry Sanford High School, and I can't wait to get into this discussion with you. We're going to start off by warming ourselves up, discussing about what is electrical resistance to refresh our brains. Electrical resistance is a measure of how much an object resists the flow of charge. And resistance also depends on the physical shape of the object through which the charge is passing. So two objects can have different resistances even if they're made of the same material. And electrical resistance is measured in units of ohms, which has a symbol of capital omega. You're going to see that very frequently. Looking at some examples, here in this example, you can see that as we increase the resistance of the component in the circuit, that the amount of charge flowing through is decreased because the resistor is resisting the flow of charge through the circuit. So the current is decreasing. Here, we can see that the physical shape of the resistor matters. In this case, we're looking at some conductive paper. And what we're going to do is look at how the resistance of the paper is going to increase as we change the length. The separation of the two probes changes the length of the path that the charge has to flow through. And we can see that as the length is increased, that also the resistance is increased. If we were to plot this data and then slide that spit line through it, we can see it's pretty linear. And it shows us that length increases the resistance of a material. So the longer the distance that the electricity has to flow through the material, the greater resistance you will have to the flow of electricity. Now we can look at a different dimension of shape, where we're going to look at instead the width of the resistor. So here you can see that just by making the resistor wider, we've essentially changed the cross-sectional area of the resistor, because now we've got more space it can flow through. So as we compare with equal lengths of wider strips, that the resistance decreases because it's easier for that charge to flow through the material when it has a greater area, a cross-sectional area to flow through. If we plot this, and we see that as cross-sectional area increases, the resistance decreases. And it's not linear. It's got a nice little curve to it, and you should be able to identify that some of those curves means that this is going to be inversely proportional. So we can graph instead 1 over that cross-sectional area, and we'll get a linear graph. So we're able to see that the resistance is inversely proportional to the area of the material. Pulling all this together, we can come up with a mathematical relationship that summarizes how the length and the area of the material affects its resistance. We have a formula in which each part describes a piece of the material, right? R is the resistance of our section of material. L is how long it is. From point A to point B, how long is that? And that'll be measured in meters if you are to plug in a number. And then what's our cross-sectional area? Almost always it'll be a circle or it'll be a nice square rectangle, something that's easily calculated if you need to calculate that area, all right? And then this fancy looking Greek letter, rho, is the resistivity of the material. And that is a property unique to that material. Every material has its own resistivity. Wood has a much higher resistivity than gold or iron does. The higher the resistivity, the less a material conducts electricity through it. So let's look at a question how this could be applied, how this might be asked to you. A rectangular strip of conductive paper of length L is measured to have a resistance of R1. The strip is then folded tightly in half. How does the new resistance R2 compare to the original value? Go ahead, pause your video, try to figure this one out on your own, and then unpause. Going through this, we know that resistance is equal to resistivity times length times area. Well, first thing we did was we cut the length in half because we folded that paper in half. So we have 1/2 L. But by doing so, we've also doubled the area, because now we have two pieces sandwiched on top of each other, so it's twice as thick. So we've doubled the area, and we cut the length in half. So we end up with 1/4 of rho L over A. So the correct answer then would be R2 is 0.25 of R1. What should we take away from this video? That resistance is a quantity that describes how much an object resists the flow of electrical charge. It's directly proportional to the length of the object, and inversely proportional to the cross-sectional area of that object. And can be described mathematically by resistance equals resistivity times length over area. Conversely, resistivity is a property of a material. It's very easy to interchange these words. They sound very similar to one another. Resistance is a property of an object describing how hard it resists the flow of electricity, and resistivity is a number assigned to the material as a whole. Be careful not to confuse the two. Thank you for watching our video today. I hope that you were able to get some clarity on how resistance is related to resistivity and how that all affects the amount of charge that flows through. Hello, welcome to AP Physics 2, AP Daily Topic 11.3, Resistance, Resistivity, and Ohm's Law, video number 2. And in this video, we will analyze experimental data to determine the resistivity of a material. I'm Mr. Blazo, coming to you from Fayetteville, North Carolina, where I teach at Terry Sanford High School. First, we're going to do is just recap what resistivity is, right? Because resistivity describes the degree to which a material resists the flow of electrical charge. It is a constant that is characteristic of a given material. It can be shown mathematically with formula resistance equals resistivity, rho, times the length of the material, L, over area. And if we look at the different parts of a material, right, we have resistance, we have length, we have a cross-sectional area, and then the resistivity, which again is a constant value for a given material. So let's look at an example of how we can experimentally determine the resistivity of a material. Whenever you're starting with a lab-based question, you want to start with a mathematical relationship that explains what you're doing. And here we know that resistance equals rho times length over area. Then we decide on a single quantity that we want to be changed, and we clearly state what quantity we are going to change. Okay, in this case, we'll change the length of the material. Then identify the quantity that will change in response to that. As we change the length, we can expect the resistance to change. So if we were to change the length, we're going to clearly state that we are going to vary the length of the material and measure the quantity of resistance. If there's other quantities that we could have chosen to change, like in this case, we could have chosen area, clearly state that you're going to keep those constant. So then we will measure the length of the material using a ruler, measure the resistance using a digital multimeter. Any tools you plan to use, you need to clearly state which tools you're going to use. And if it's anything more complicated than a meter stick or a ruler, sometimes it helps to explain how to use it. All right? Repeat for different lengths of material, keeping the cross-sectional area constant. If you're worried that your procedure may be slightly unclear, it's always good if you throw in a small sketch of your setup. Doesn't have to be art, but sometimes a little bit of a sketch of your laboratory setup can make it clearer what your procedure is indicating. So once you've collected your data, right, we need to analyze it. So we need to figure out how we can plot this on a graph. If we are analyzing, we are plotting our data on a graph, normally in an attempt to use a best fit line to find our unknown. So we can take our data here, here's our formula, and we'll just compare it to the classic y equals mx plus b. And we can see that if we place r on the y-axis and we place length on the x-axis, well, that means the slope must be rho over a. And both of those are constants. Rho is a constant of the material, and a we chose to keep constant. So when we plot our data, we'll end up with a nice straight line, the slope of which is rho over a. So we can then calculate the slope of that line and use rho over a to determine the resistivity of the material. As far as reducing experimental error, it's always important to include steps to reduce error, to improve accuracy. And it's as simple as saying repeating the resistance measurements on the same material multiple times, or comparing resistance measurements of the same experimental material between different lab groups. In general, finding a way to repeat the measurements helps to reduce experimental error. Let's go ahead and look at a practice example of how we would address a lab-based question about resistivity of a material. What measurements would you make if you were to conduct a similar investigation in which the material's length was kept constant? Go ahead, pause the video, jot down real quickly what you would do, what you would measure in order to determine a procedure for keeping length constant. The first thing we do is we'd use a ruler to measure the dimensions of the cross-sectional area of the material. If you're using something very thin, like a piece of conductive paper, a ruler might not be an appropriate tool. You may have to pull out a caliper or something smaller for measuring very thin materials. Make sure that the tool you're using to make the measurement is appropriate for the measurement you're trying to make. Then we could say we would use a multimeter or similar device, we would name what we're using, to measure the resistance of the material as we vary the area. So a follow-up question then would be, well, what quantities would you graph to produce a best fit line that can be used to determine the resistivity of the material? Go ahead, pause the video, and see if you can determine which quantities should be plotted on the x and y axis that would give us a best fit line that we use to find the resistivity. Starting from our known mathematical relationship, we know that we varied A, we kept L constant. So we're trying to group things together. So we're going to group what we kept constant together, the rho and the L, and push to the side that which we varied. Compared to y equals mx plus b, our y-axis is going to be resistance, our slope will be rho times length, and then 1 over area would be our x-axis. Not area, but 1 over area. So we'd end up with a graph with resistance on the y-axis, 1 over the area on the x-axis, and the slope would be rho times length, which we kept constant. So what should we take away from resistivity in the lab? First, you always start with a mathematical relationship that kind of guides you on what quantities to keep constant and which quantities you will vary. In this case, we use resistance as our dependent variable, the one that changed in response to us changing either length or area. Never change two variables in the same lab setup. Choose one variable to change. Describe in your procedure how each piece of equipment is used and what values they are used to measure. Be clear and say you use a ruler to measure the length of the material. Create a graph using that data from which a best fit line can be used to determine whatever constant value we are looking for. And then repeat your measurements in order to reduce experimental error. Thank you for watching this video today. I hope that you gained some skills about how to approach resistivity. Hello, welcome to AP Daily for AP Physics 2, topic 11.3, resistance, resistivity, and Ohm's law. Here in video number 3, we will explore the relationship between current, resistance, and voltage as exemplified by Ohm's law. I'm Mr. Blazo, coming to you from Fayetteville, North Carolina, where I teach at Terry Sanford High School. Let's start by warming up with some key quantities and terms. Right? Whenever we're analyzing a circuit, we've got a schematic design here of a very small circuit composed of one resistor. First quantity that's going to matter is going to be I, which is our current. It's the amount of charge that passes a given point in the circuit every second. It is measured in units of amperes, A. And sometimes it's shown as Q over T, how much charge that passes through the battery in a given amount of time. You use the current to determine that value. And we show this in our schematic drawing with an arrow showing the numeric value of the current. The second quantity that matters is going to be our resistance, R. And this is how much a component resists or inhibits the flow of charge. It's measured in ohms. We indicate this with an R, or again, the numeric value if we know it. The second is the potential difference, right, which is denoted by delta V, which is change in potential. Sometimes you'll see it as a epsilon. Generally, if it's from a solid-state power source, from some sort of battery or other power source, you might see an epsilon indicating it. Don't be thrown off. It works exactly the same way. This is the change in electric potential between 2 points within a circuit, and it's measured in volts. We remember that this is between 2 points in the circuit. It could be across the battery, in which case we get the voltage of the battery. It could be across the resistor, in which case we get the change in electric potential as the current passes through the resistor. There are some other synonyms that will plug into Ohm's law very similarly. You may see voltage. You may see electromotive force, which also tells us the change in potential. Or you may see voltage drop. All of these terms refer to the same thing, the change in potential across 2 points within a circuit. So let's look at an example of how potential difference affects current. So in this simulation, we can see that as current in the circuit increases, the potential difference must also be increasing. So as we control the voltage, we can see that the current increases. If we go ahead and graph this, we can find that we have a nice, directly proportional linear relationship between potential difference and current. Conversely, if we are to look at resistance versus current, here in this simulation, you can see that as we increase that resistance, that the current decreases because the resistor is fighting the flow of electric charge through its component. If we go ahead and graph these values, we find that we get a decreasing, inversely proportional graph showing that resistance is inversely proportional to the current flowing through it. Tying all these together, we can build Ohm's law, which tells us that current is equal to the change in potential over the resistance of the circuit or a circuit component. The most challenging part about Ohm's law in circuits is that you use it all the time. It's the single most used formula when analyzing circuits. And so because it's used, sometimes it's difficult to keep in mind which voltage, which resistor, which current. Because as circuits get more complicated, they all go into the same formula. You won't be cherry picking looking for another formula. You're always looking for Ohm's law. And we'll dig into some more complex circuits in later videos. From here, though, we can see that as the potential difference increases, if it were doubled, well, the current would also double. And if we double the resistance, well, that 2's tucked in the denominator, so we're dividing by 2. So we would cut that current in half. Electric circuits and components like resistors that follow this relationship are called either ohmic or ideal. All right, so if they follow Ohm's law, it's called an ohmic circuit. Don't get all tied up if you hear that word in a sentence. They're just saying, hey, this circuit follows Ohm's law. And you can always assume that circuits and components are ohmic unless they state otherwise. So let's go ahead and practice by looking at how we can rank the current flowing through a circuit using Ohm's law. In this case, which of the following correctly ranks the current drawn from the battery in the circuits shown? Go ahead, pause the video, take a moment, try and figure out what the order is for ranking the different currents drawn from the battery. We're going to go ahead and use Ohm's law to try to identify what the current is relatively. We don't have any numbers. We can't plug anything in. We do have some information. For the first one, we have the current has to equal V over R. They're just V and R. That's all we have. For the second one, moving down, we can see that current B is equal to V over 2R. So that's going to be 1/2 of VR. So we already tell that one must be less than our first one. For the next one, we have voltage over 1/2 R. And since we're dividing by half, we can go ahead and change that to current equals 2 V over R. Because we divide by half, it's the same as multiplying by 2. In our fourth circuit, you can see that we have 1/2 of the voltage over R. We can pull that 1/2 out to the front to get 1/2 V over R. And in doing so, we can see that our smallest value is 1/2 V over R. Both current B and current D have that smallest value. So IB must equal ID, which eliminates A and eliminates D from our answer choices. And then when we compare the other ones, the next largest is current A with V over R, and then current C is the largest with 2 with V over R. So here we are, selecting B as our correct ranking. What should we take away from this video? We should take away that Ohm's law can be shown mathematically, where current is equal to the change in potential over the resistance of a component in a circuit or a section of the circuit. Current is directly proportional to the potential difference. As potential and voltage increases, the current increases directly with it. It is inversely proportional to resistance. As resistance increases, the current through that section of the circuit, through that component, decreases. Any electrical circuit or component that follows this relationship is considered to be ohmic or ideal. We always assume that wires and circuit components are ohmic unless it's otherwise stated within the problem. Thank you for watching this video today. I hope that it helped to clarify the relationships between resistance, current, and potential difference as exemplified by Ohm's law. Hello, welcome to AP Daily for AP Physics 2, topic 11.3, resistance, resistivity, and Ohm's law, video number 4. In this video, we're going to examine the effects of how resistors convert electric energy into thermal energy, as well as how to determine whether or not a specific component within a circuit is ohmic. I'm Mr. Blazo, coming to you from Fayetteville, North Carolina, where I teach at Terry Sanford High School. We're going to start off by reviewing resistivity and Ohm's law. Remember that resistivity describes the degree to which a material resists the flow of electrical charge, and is shown mathematically through the relationship of resistance, length of the wire or component, the cross-sectional area, and the resistivity of the material. Ohm's law describes the relationship between potential difference between 2 points within a circuit, the resistance, and the current. It can be shown mathematically with V equals IR, where I is the current, V is the potential difference, and R is the resistance. Remember that we'll be talking about 2 points in a circuit, not the entire circuit as a whole every single time. Ohmic resistors follow Ohm's law, which means the material will have a constant resistivity and will have a constant resistance. Here we have a resistor that as we turn up the voltage, the current goes up. I equals V over R means that if we graph this, we'll get a nice straight linear graph, whereas voltage increases, current increases. And the slope of that graph will be 1 over our resistance. Let's look at an example. We've all experienced with our phone chargers, computer chargers, other devices that they heat up while they're plugged in and in use. Here I got a regular old computer charger, and you can see it's much warmer than the ambient temperature. My room is not 96 degrees. So you can tell that this is dissipating thermal energy. And circuit breakers in your house work by the same principle. If too much current is drawn through them, they heat up, which is what causes them to pop. They don't actually notice too much current, they notice too much heat being dissipated. So the trick is that when conductors increase in temperature, when they're dissipating all this extra heat, the resistivity of the material tends to increase. And with increased resistivity, then the resistance of the wire resistor, other components, must also increase, which means that it will dissipate even more heat, increasing its resistivity. A little bit of positive feedback loop, where just the heat dissipating itself will make the component have more resistance, which means it's no longer ohmic. So suppose we want to collect data to test whether or not a resistor obeys Ohm law. But as more current flows through the resistor, it heats up. Well, remember, current is 1 over resistance, and resistance is related to resistivity, that rho value. So as we increase the voltage, we increase the current, the resistor starts to heat up, and we end up with a graph that right off the bat might look pretty straight. When we try to draw a best fit line through it, well, can't connect the ends. We try to put our line up near the top, it fits up there a little bit. Maybe we can roll it on down to the bottom. We can get it to be a little straight there. It's no longer linear. So if you ever identify a graph of voltage versus current, right, representing Ohm's law, and it's not linear, that means your resistance is changing, and that your component is no longer ohmic. It's no longer ideal. So let's look at a question that we could ask that would represent this. A student is doing investigation about Ohm's law and plans to collect data about current passing through a resistor at various voltages. First, sketch a qualitative graph that predicts the relationship between current and voltage for an ideal resistor. Go ahead, pause the video, and give a quick qualitative sketch. You'll see right here, it should be nice and straight and linear. It should have a positive slope because as voltage increases, current increases, and it's a constant slope. It's a straight line. When we say a qualitative graph, it doesn't necessarily have numbers. We're looking for the shape of the line. Is it straight? Does it have a curve when it needs to have a curve? So a qualitative graph is different than a quantitative graph, in that we're looking for the shape that demonstrates the relationship between the quantities. Carrying on, a student instead, when they measure their data, they get this graph. So how does this graph deviate from Ohm's law, and what could be a physical explanation for this result? Go ahead, pause the video, sketch down an answer. And it deviates from Ohm's law because the slope is decreasing, which means that the resistance must be increasing, because 1 over R is our slope. And we know that it should be a constant line. An explanation for this is that the resistor may be heating up, which is increasing the resistivity of the material, causing the resistance to change. Or it could simply be that the component itself is not ohmic, that its resistance varies with voltage or varies with current. If it states that the temperature remains constant, that's the only other possible option. What should we take away from this video? We should remember that when conductors heat up, their resistivity increases. Thus, the object's resistance increases. Remember that resistance is resistivity times length over area, and if that resistivity value increases, the resistance must also increase. There's a functional dependence there. If experimental data for current versus voltage isn't linear, then one of two things is true. That resistor is heating up and the resistivity is increasing, or the resistor is simply not ohmic if the temperature remains constant. Thank you for attending today's AP Daily video. I hope you found it informative, and I look forward to seeing you on future videos about electric power. Hello, welcome to AP Daily for AP Physics 2, topic 11.4, electric power, video number 1, and in this video we will consider the rate at which an electrical circuit dissipates energy. Hello, I'm Drew Blazo, coming to you from Fayetteville, North Carolina, where I teach at Terry Sanford High School. We need to revisit power. You will learn about this in AP Physics 1. We will discuss that this is the rate at which work is done, or the rate at which energy is transferred. When we're talking about electrical power, we're talking about the amount of energy that is transferred from an electrical source into another source. So power is measured in units of joules per second, and that is also known as watts. So remember, you see power all over the place when you're experiencing your life. You might see it on a power charger for your computer. Here I've got my computer charger up here. You can see it says 45 watts. So it is transferring 45 joules of electrical energy every second between the outlet and the computer. Here we have a light bulb, which is labeled 5.5 watts. So it's converting 5.5 joules of electrical energy into light and a little bit of heat every second, which is dissipated into the surroundings. These do give rise to some unexpected units. You may have seen, perhaps on your parents' electric bill, a kilowatt hour, which seems like it's going to be a unit of power. But let's look at this more closely. That's kilowatts times hours, which is going to be kilojoules per second times hours over 1. If we do a little bit of dimensional analysis with that, you can see, well, that's energy over time multiplied by time. Time's going to cancel out. And you're really looking at is a unit of energy. So the kilowatt hour is sneakily a unit of energy. And if you do a little bit of dimensional analysis, you can convert a kilowatt hour into a joule. So when we're looking at circuits, we're going to look at one resistor in the circuit. So we have a resistor, and it's going to have current flowing through it, and it's going to be a potential difference across the circuit. For that single resistor, right, the power dissipated is equal to the current times that change in potential across the resistor. Keep in mind, big time, do not assume that the change in potential for that single resistor is the same as the battery. All right, different components will have different potential differences across them in the circuit. Do not make that assumption. Over here, if we were to look at just the voltage across the battery, that would be the power dissipated by the entire circuit. If we had multiple resistors, multiple components, that battery potential difference and its current will be used to get the power dissipated by the entire circuit, not just one single component. When we combine this with Ohm's law, we can do some really helpful substitutions. If we take P equals IV and we go to Ohm's law, we can substitute in for I and rearrange to get P for power equals the potential difference squared over R. Additionally, we can substitute in for the V, and we can get power equals I squared times R. All of these are valid equations used to calculate power. Power equals current times voltage, current squared times resistance, and voltage squared over resistance. If we know any two of these values, if you know the resistance, the potential difference, and the current, out of those three, you know two of them, you can calculate the power dissipated by that component or that area of the circuit. So let's practice by looking at a situation where we're going to rank the power dissipated by number of resistors from greatest to least. Here we've got 5 different resistors. Go ahead, pause the video, and see if you can rank these resistors from greatest to least power dissipated. The first thing you need to do in order to properly rank these is to choose the correct relationship for power. We have power is current times voltage, it's voltage squared over resistance, and it's current squared times resistance. Looking at the values we're given voltage and resistance. So that's going to be the formula we choose to make our comparison. So look at the first one, it's simply V squared over R. B is going to be 2V squared, which means we got to square the V and the 2, which is why we end up with a 4 hanging around out front. For C, we have V squared over 2R, so that's why we're multiplying by a half. D is going to be 2V squared, so we're going to have 4 on the top, and then we got 2 on the bottom, divided out, we get a 2. And then over here we have 2V squared, we have 4 on the top, we have 4 on the bottom, they cancel each other out to be V squared over R again. Then we can simply rank them from greatest to least by looking at those little coefficients we pulled out to the front of our fraction. We end up with B is greater than D, A and E are equal, and then C is the least of all. So what should we take away from this video? Electrical power is the rate at which energy is transferred or converted within an electrical system. It's measured in units of joules per second, or watts, and power is directly related to the current in the resistor and to the potential difference across that resistor. We can make substitutions using Ohm's law to end up with other useful equations for power that allow us to calculate it if we know any two of the Ohm's law values. Thank you for coming out to this video today. I hope you found it informative and useful, and I look forward to seeing you in our Hello, welcome to AP Daily for AP Physics 2, topic 11.4, electric power. And in this video, we're going to examine how we can qualitatively represent the electrical power using graphs and the brightness of a light bulb. I'm Mr. Blazo, coming to you from Fayetteville, North Carolina, where I teach at Terry Sanford High School. Let's go ahead and we're going to warm up by just looking at Ohm's law and how it relates to power. Suppose we connect a light bulb, resistance R, to an adjustable power source, so we can turn a knob and increase that voltage. What would happen to the potential difference across a light bulb if we increase the current? Recall from Ohm's law that V, potential difference over R, equals current. So if the current increased, that means that we must have also increased the voltage. For example, we doubled it. The potential difference would double. So what does that do to the power dissipated by the light bulb? Well, we can look at our equations here. We can do a little bit of substituting because we know all the different values. And we see that power in every case increases by 4. So if we double the potential difference, we quadruple the power dissipated. So it's not a linear relationship. Let's look at some examples. For a given light bulb with a constant resistance, we're assuming it's an ohmic light bulb, power increases with the current flow and potential difference because of the squared term in the equation. So we end up with graphs that look like this, where it's sloped upwards. If you ever have to do a calculation where you need this graph to be straight, well, instead of using I and V for our graphs, we can graph I squared and V squared, and we will be given a nice linear graph, which we can then use our best fit line method to figure out a constant value. If we look at the resistance, though, resistance is on the bottom, so we have a inverse relationship where it's a decline. So if we do a little bit of rearranging on this one, and we use 1 over R on the bottom, because we can pull that term out to the front, then we will also get a linear graph. This process is called linearizing your graph and is very useful when you need to use the slope of a best fit line to determine some quantity. So if we look at light bulbs and their brightness as related to power, for any given bulb, it's going to give off some amount of energy as visible light, and some is going to be converted into thermal energy. The bulb is going to warm up. So for example, a 40-watt light bulb will convert a total of 40 joules in a combination of visible light and thermal energy, heat, every second. It might be 2 watts of light, visible light, versus 38 watts of thermal energy. It depends on the efficiency of the light bulb, right? But it's going to go ahead and give off that much energy. So as we ramp up the power in a light bulb, you'll see that the brightness changes. And here in this example, you can see that as we turn up the voltage on this light bulb, eventually the light bulb will burn out, but the brightness is increasing. We have a voltmeter and we have a light sensor measuring both quantities as we increase the voltage. So for a light bulb, we can qualitatively look at it and say, well, the brighter the light bulb is, the more power it is dissipating. This is super important, though. It is only a qualitative relationship. We can say the light bulb got twice as bright so that it got twice as much power. This is a qualitative relationship. Here's a graph of voltage versus brightness for the experiment I just ran in the last slide. You can see that it slopes up and then it kind of dips off when the light bulb dies. It's not a nice linear relationship, and it varies from light bulb manufacturer to light bulb manufacturer. The thing you can count on, though, is more power means more brightness. So let's practice by trying to rank the brightnesses of a number of different light bulbs based on information about the voltage and the current flowing through them. So we know that power equals IV, it equals V squared over R, and it equals I squared times R. In this case, we're going to choose the first equation because we're given voltages and we are given currents. Go ahead and take a moment to try to rank the relative brightnesses of light bulbs in this example. We can take a look at them one at a time. The first one is just I times V. Second one's going to be 2I times 2V, so 4 IV. And then we have a half V times a half I, so we give us a quarter IV. Here we have 2 times I times a quarter of V, gives us a half IV. And here the power is going to be 2 because we have a half times 4. We're just really looking at those leading terms to see how they're going to go ahead and adjust and scale our power output. From here, we just rank them from greatest to least power. And that will tell us the relative brightnesses of them. It's not going to tell us one's twice as bright, 3 times as bright, but it will tell us which ones are brighter than the others. So what should we take away from this video? Well, first off, that we can look at graphs on power in order to determine for a given light bulb that if as long as it's constant resistance, power increases with the current and the potential difference. All right, for the same power source, it's going to decrease with the resistance of a light bulb. If we replace one light bulb with another with greater resistance, the power output will decrease because the current flow is going to decrease. And we can remember that light bulbs are going to convert electrical energy into both visible light and some amount of thermal energy or heat, and that we can qualitatively determine their power output by comparing the brightness of the individual light bulbs. Thank you for watching this video today. I hope that was able to help clarify some of the intricacies of how power can be qualitatively.
Hello, and welcome to AP Physics 2, algebra-based daily video, topic 11.5 on compound direct current circuits. In this video, we will use a simulation to demonstrate the differences between series and parallel circuits. My name is Mike Betsko, and I'm an AP Physics teacher at Mills E. Godwin High School in Henrico, Virginia. Let's take a moment to review what we previously learned. In a daily video, you learned about Ohm's law and the relationship between voltage, current, and resistance as given by the formula V equals IR. In this video, I'm going to teach you about one specific aspect of the equation, how the resistance of the circuit can be changed simply by connecting the elements in different ways. So let's look at an example using the FET simulation. So as you can see in this circuit, we have one battery and one light bulb connected with a series of wires. The red arrows in this instance represent the conventional current that is moving through the circuit. Take note of the direction that the red arrows are moving in, as well as the rate at which those red arrows are moving as well. We will use this information later. Also, the yellow lines around the light bulb represent the brightness of the light bulb. The more lines there are, the brighter the light bulb appears to be. So you may ask, how do we add a second light bulb to the first one? And what effect would that have on the circuit itself? So if we add a second light bulb, like this here, you can see that what we have is that the current that is moving through the circuit is going to move through light bulb number 1, then light bulb number 2 on its way back to the battery. The red arrows again are representing the direction of the conventional current, and the rate at which those red arrows are moving, we should note, is exactly the same in all parts of the circuit. But of interest is the fact that the red arrows now appear to be moving at a slower rate than they were in the previous circuit. So what does that tell us has happened to our circuit? Well, if the current has decreased, then we must assume that the resistance of the circuit has actually increased. Ohm's law tells us V equals IR, and if V is constant, we haven't changed the battery, and the I appears to have decreased, then that tells us the resistance of the circuit has increased. So that means that in a series circuit, as we add light bulbs, what is actually going to happen is the resistance of the circuit is going to increase. The current flowing through the circuit also shows up in the brightness of the light bulb. Notice the number of yellow lines around the light bulb has decreased. This tells us that the brightness of the light bulb has decreased as well. Each light bulb goes with the same brightness, but since they're getting the same current, they must be the same type of light bulb as well. So what do we take away from a series circuit? That as we add light bulbs in series, then the resistance of our circuit goes up and the current goes down, and the brightness of our light bulb will go down as well. Another interesting feature of a series circuit is that if I come over here, I can actually disconnect the circuit. What do you think is going to happen when I disconnect the circuit to the brightness of the light bulbs? Well, if I click here, I break the circuit open, and you'll notice that now we do not have a closed circuit, we have an open circuit, and as a result, our light bulbs are actually going to go out. So any series circuit, any break in the path will actually cause the entire circuit to stop functioning. Is there a second way that we can add a light bulb to the first light bulb? And what changes would that make within our circuit? In this situation, you will see that the second light bulb has been added in parallel to the first. How does this affect the brightness of the light bulb and the current through the circuit? Well, if I look through each individual branch, I should note that the current is going to be similar to the first circuit, and not like the second circuit. It's actually now moving a little bit faster. The brightness of the light bulb is again much like the first circuit and not like the series circuit light bulbs. They appear to be brighter than they were before. The current through the battery appears to be moving faster than it is in the other two parts of the circuit where the light bulbs are. What does this tell us? Well, somehow the resistance of my circuit has actually decreased, causing the current through the battery to actually increase. So what this tells us is that as we add resistors in parallel, the resistance in total of the circuit actually is going to decrease, which then causes the current in the battery to actually increase, which is of course different than it is in a series circuit. Now, what's going to happen if I break the circuit apart? Well, what do you think is going to happen? Well, if I cut the circuit down here, notice that only the branch that is affected by where the cut is, or the break in the circuit appears, is going to turn off. The other light bulb continues to glow as if nothing has happened. Same brightness and the same rate of charge flow or current is going through that branch. So what should we take away from the simulations that we just looked at? What is the difference between a series circuit and a parallel circuit? In a series circuit, they are arranged such that the current has only one path to follow throughout the entire circuit. The current in the series circuit is the same throughout the entire circuit as it travels from one circuit element to the next on its way through the circuit. And then finally, when resistors are added in series, the resistance of the entire circuit is going to increase. A break in a series circuit will cause all the elements in that circuit to actually stop working. In a parallel circuit, they are arranged such that the current has multiple paths to follow through the circuit. When resistors are added in parallel, the resistance of the entire circuit will actually decrease. The current in each branch will remain the same, but the total current that is moving in the battery will actually increase. And a break in the circuit will only cause the circuit elements in that branch to stop working, and the rest of the circuit will continue working exactly as before. Thank you very much. Hello, and welcome to this AP Physics 2 daily video on topic 11.5, compound direct current circuits. This is daily video number 2, and in this video, we will discuss how to draw a circuit diagram and determine equivalent resistance for series and parallel circuits. My name is Mike Betsko, and I'm an AP Physics teacher at Mills E. Godwin High School in Henrico, Virginia. So let's review. In video number 1, we discussed the properties of series and parallel circuits. Simply stated, series circuits provide one path for the charge to move through, and parallel circuits provide multiple paths. So let me ask you two questions. Question number 1, how do we represent the image to the right as a schematic diagram? I don't think we want to draw the batteries and the light bulbs over and over and over again, so there must be an easier way that we can all agree upon to represent a circuit in a simpler manner. Secondly, how do we analyze the circuit to determine the equivalent resistance? In other words, when we have all these resistors added to a circuit, how do we find out what the total resistance of the circuit happens to be? So first, let's look at an example. In this circuit, we have a battery connected to 3 light bulbs. How would we represent this simulation circuit as actually a schematic circuit? So it would look something like this. A battery is represented by 2 or more parallel lines, one long parallel line and one shorter line. The longer line represents the positive side of the battery and the shorter line represents the negative side. The wires are just represented by solid lines, and then the light bulb is some sort of a circle with either a label or a circular line inside of the bigger circle. There are 3 circles representing that there are 3 light bulbs in the circuit. Well, what if we replace our light bulbs with resistors? And the circuit would look something like this. Well, in our circuit diagram, it's going to look like this. Notice the battery looks exactly the same, but now our light bulbs are replaced with resistors, and our way of representing resistors are with these jagged lines. So again, we have 3 resistors, and we have 3 different resistors represented in our circuit diagram. A parallel circuit, represented by 3 light bulbs in this image, would look like this as a schematic or a circuit diagram. Again, the battery and the 3 light bulbs. And then finally, if we had a simulation circuit with 3 resistors, our circuit diagram would look like this: a battery and then the 3 resistors in parallel to the battery. So drawing circuit diagrams are not all that difficult, and you will learn as you learn more circuit elements how to represent those in the circuit diagram. But for now, we're going to move on and we're going to talk about finding the equivalent resistance. So what happens to the resistance in the series circuit as resistors are added? You might recall from daily video 1 that what we said was that as we add resistors in series, the total resistance of the circuit is actually going to go up. So here, what we're going to do is we're going to represent that mathematically by simply saying that R sub S, in other words, the resistance of our series circuit, is equal to R1 plus R2 plus R3. On the equation sheet, you will see this relationship. On the equation sheet, you will see this relationship is represented as R sub S is equal to the sum of all the individual resistors. What about in a parallel circuit? Now remember, in a parallel circuit, that when we added resistors, the resistance actually goes down and not up. So mathematically, this can be kind of confusing. In a parallel circuit, in order to find the total resistance or the equivalent resistance, what we're going to do is we're going to add the reciprocals of the resistors. So we're going to end up with an equation that looks like this: 1 over Rp is equal to 1 over R1 plus 1 over R2 plus 1 over R3. On your equation sheet, that equation will look something like this: 1 over Rp is equal to the sum of the reciprocals of each individual resistance in your circuit. So let's practice. If we were given this circuit shown to the right, how would we find the total resistance of the circuit? Our goal is to replace all 3 of those resistors with one resistor that we can say is the equivalent resistance for the 3. The first thing we must do is identify what type of circuit it is. In this case, we can see that the resistors are connected in series with one another, and so we're going to use the equation for series resistance. Right? So R sub S is equal to R sub 1 plus R2 plus R sub 3. We simply then substitute in the values for each one of the individual resistors, 2 ohms plus 4 ohms plus 6 ohms, and the total resistance of the circuit would then be 12 ohms. What if we added our resistors in parallel? Okay, again, we should note that this circuit is different than the previous circuit because this is in parallel rather than in series. So once I identify what type of circuit it is, then I just use the proper equation. In this case, 1 over Rp equals 1 over R1 plus 1 over R2 plus 1 over R3. Substitute in the given information: 1 over Rp equals 1 over 2 plus 1 over 4 plus 1 over 6, and I end up with that 1 over Rp is equal to 5.5 all over 6. But there's one more step that we want to do. We want to find what the equivalent resistance is of the circuit. In other words, what's the value of a single resistor that I could use to replace the 3 resistors in our given circuit. So in order to do this, I need to do one more step. I want to take the reciprocal of 5.5 over 6, which will then tell me the value of R sub P, or my parallel resistance. So I'm going to hit that reciprocal button one more time on my calculator, and I will find that R sub P is equal to 1.1 ohms. So what should we take away? Well, in equivalent resistances, a set of resistors in series is simply the sum of the individual resistances. When resistors are connected in series, the equivalent resistance will actually increase. The inverse of the equivalent resistance of a set of resistors connected in parallel is equal to the sum of the inverses of the individual resistances, as given by the equation below. And when resistors are connected in parallel, the equivalent resistance will actually decrease. Thank you very much. Hello, and welcome to this AP Physics 2 video on topic 11.5, compound direct current circuits. This is daily video number 3, and in this video, we will derive an equation to model what happens when a battery has internal resistance. My name is Mike Petsko, and I'm an AP Physics teacher at Mills E. Godwin High School in Henrico, Virginia. Let's review. Hope you remember the video on Ohm's law and the equation below, V equals IR. In this video, we are going to use Ohm's law to help us learn about the internal resistance of a battery. Let's take a look at an example. As you can see in this circuit, we have a simple circuit. There is a battery, and a switch, and a light bulb. Since the switch is open, there is no current flowing through the circuit. We also have 2 devices that are going to help us make measurements of the circuit itself. We have a voltmeter, which will measure the voltage across each circuit element, and we have an ammeter, which is going to allow us to measure the current flowing through the circuit as well. I can actually measure the voltage of the battery simply by taking the 2 probes and place them on either side of the battery. You will note that the battery has a voltage of 9 volts. When I close the circuit, then the charge will begin to flow through the circuit, and the ammeter will actually read a value. In this case, you will see it's 0.45 amps. So this is a simple circuit, and the light bulb, of course, is now going to glow. Of interest to us in this video is what's going to happen within the battery itself. As I hope you know, the battery is going to not work as well over time. This is why we must replace them after a few months of use. Why does that happen? Well, it happens because resistance develops within the battery itself. And so over on the side here, we can actually change the resistance of just the battery by moving the slider a little bit. And when I move the slider, you're going to note that the voltage is going to be different, and the current is now going to be different. Well, the reason those 2 values are different is because there is now an added resistance within the battery itself. And if I increase the resistance a little more, you can see the current is going to change as well as the voltage that is supplied to the circuit. If I increase the resistance, you can see there's a trend developing. As the resistance increases, the current moving through the circuit is going to decrease, and the voltage supplied to the circuit is going to decrease as well. And we can keep on going. And of course, we get to a point, maybe right here, where we have a 7.2 volt battery in terms of what's being supplied to the circuit and 0.36 amps worth of current. So let's go back to the PowerPoint to make sense of all this new information. What we should note is a pattern has developed. As the battery resistance increases, the battery voltage decreases, and the current is going to decrease. If we recorded all the information as we did work through the simulation, we might develop a data table that looks something like this: the voltage measured in volts, the current measured in amps, and the battery resistance measured in ohms. We can note that as the battery resistance increased, the voltage decreased as well as the current. If you can remember what the numbers are in blue, we're going to be using those to highlight an example of this internal resistance. So if we go ahead and say, all right, the potential difference of the battery when there is no charge flowing through the circuit is 9 volts. The voltage supplied to the circuit by the battery did decrease, though, as the battery resistance increases. So let's call this the terminal voltage. So what we can identify is that the battery voltage, when there's no charge flowing at all, is equal to the sum of the terminal voltage, and then there appears to be some missing voltage that we haven't factored into this discussion. So what accounts for that missing voltage? Well, let's go ahead and replace the missing voltage with I times R, because V equals IR is given to us by Ohm's law. So the battery voltage then is equal to the terminal voltage plus I times R. Now remember that data that I asked you to remember that was in blue? Let's substitute that information in. So the battery voltage was 9 volts. The terminal voltage, what was actually getting across the circuit, is 8.18 volts. And the current that's measured by the ammeter moving through the circuit is 0.41 amps. And then little r, which is we're just going to say is the battery resistance, is our unknown. If we solve for little r, we end up getting a result of 2 ohms. What is little r? Well, it's the internal resistance of the battery, and it's defined as the opposition to the movement of the charge within the battery. And if you remember from our data table, that 9 volt and the 8.18 volt and the 0.41 amp had a battery resistance of 2 ohms. So what should we take away? The internal resistance R of a battery increases over time due to physical and chemical factors within the battery. The internal resistance of a battery can be determined using the following equation. The terminal voltage is simply equal to the voltage of the battery. In other words, when you buy this battery in a store, that's what you expect to actually get if there was no internal resistance at all within the battery, minus I times R. I is the current moving through the circuit, and little r represents the internal resistance of the battery. Internal resistance adds in series to any other resistors in a circuit and will increase the equivalent resistance of the circuit. Ideal batteries typically have negligible internal resistance. Thank you very much. Hello, and welcome to this AP Physics 2 daily video on topic 11.5, compound direct current circuits. This is daily video number 4. In this video, we will discuss how to correctly place ammeters and voltmeters in a circuit. My name is Mike Fesko, and I'm an AP Physics teacher in Milty Godwin High School in Henrico, Virginia. Let's review. What do you remember about series circuits? Well, hopefully you remember that there is only one path for the current to move in a series circuit. Secondly, the current throughout the series circuit will always be the same. And also, as resistors are added in series, the equivalent resistance of the entire circuit will increase. What do you remember about parallel circuits? Well, in a parallel circuit, there are multiple branches or paths for the current to take in that circuit. The voltage across each branch of the parallel circuit is actually equal, and as resistors are added in parallel, the equivalent resistance will decrease. So let's look at an example. In this example of a parallel circuit, what we should see is that we have a battery connected to 2 resistors. Also, we have a voltmeter and an ammeter, which we're going to use to correctly measure the voltage and the current at various points around the circuit. In order to measure voltage, what we're going to do is take our probe and we're going to place it in parallel with the element that we are trying to measure the voltage across. Notice the battery is a 9-volt battery. Well, what would we expect to see is the voltage across the individual resistors? For us to figure this out, we simply take the probe, place it on one side of the resistor in parallel with the other side of the resistor, and we can say that the voltage across the resistor is given by 9 volts, or negative 9 volts, since the resistor is actually taking the voltage away. What would we expect the voltage to be across the second resistor? Well, if we go ahead and use our probes and place them on either side of the resistor, we will note that 9 volts of potential is lost in that second resistor as well. This makes sense because 9 volts is supplied by the battery, and then the charge that goes down the first branch must lose the 9 volts as it goes back to the battery. It does not ever encounter the second resistor. And the charge that goes through the second resistor must lose all 9 volts as well, because it too goes directly back to the battery. Now, how do we measure the current? Well, an ammeter must be placed in series with the device that we are trying to measure the current through. So what I'm going to do is to show you what would happen if I actually put an ammeter in parallel with a circuit element. So I'm going to connect this ammeter with a wire and connect it in parallel to the last resistor. Notice what we've just done is we create a short circuit. The charge is flowing at a ridiculously high rate, and the battery is now on fire. Okay, so we don't want to do that. So what we're going to do is we're going to remove this from our circuit, and we're going to properly place the ammeter so that we can make the measurement of the current through each part of the circuit. So let me get my ammeter back again. So in order to measure current, the ammeter must be placed in series with the circuit. So I'm going to break the circuit open, place the ammeter in the circuit itself. Notice that it's now in series, right? The charge is going to flow through the ammeter as it goes to the resistor. Notice the current is being measured at 0.9 amps. Okay, well, so that's the current down this branch. So what's the current down this branch? Well, again, I'm just going to simply take it out, reconnect my circuit so that there is charge flowing through both branches of my circuit, and I'm going to open up the circuit over here, place my ammeter in series with that resistor, and notice again, we end up with a value of 0.9 amps, telling us that there's 0.9 amps of the current going down this branch, and there's 0.9 amps worth of current going down this branch. Why is it 0.9 amps down each branch? Well, the reason it's 0.9 amps down each branch is because the resistance of each resistor happens to be the same. If I change the resistor, say for example, I take this one out and I put another one in its place, okay, and I change the value of its resistance, notice that the current will actually increase or decrease as I change the resistance of that resistor. Okay. Now I'm going to take that ammeter or take that resistor out. I'm going to take the ammeter out. I'm going to put the resistor back in, and we're going to now go ahead and measure the current flowing through the battery. Okay. So what do? We disconnect the circuit. We put the ammeter in series with my battery, and what do you think we're going to find is the current through this part of the circuit? If we go back to the first connections that we made 0.9 amps in this circuit. We have 0.9 amps in this part of the circuit. So what do we expect to see in this part of the circuit? Remember, those charges, the current represented by the movement of the charges, we're going to add together. So we would expect to see 1.8 amps would be the current flowing through the battery. Okay, and then what's going to happen is 0.9 amps of current goes down the first branch, and then 0.9 amps goes down the second branch. So what should we take away? What did we just learn about voltmeters? Voltmeters measure the potential difference between any 2 points in a circuit. Voltmeters must be connected in parallel with the elements across which the potential difference is being measured. What did we just learn about ammeters? Ammeters measure the current at a specific point in the circuit. Ammeters must be connected in series with the element in which the current is being measured. Thank you very much. Hello, and welcome to this AP Physics 2 video on topic 11.6, Kirchhoff's loop rule. This is daily video number 1, and in this video we will discuss how to apply Kirchhoff's loop rule and describe how it is an application of energy conservation. My name is Mike Fesko, and I'm an AP Physics teacher at Milton High School in Henrico, Virginia. Let's review. In the previous video, you learned about how electric potential energy is defined by the following equation: delta U equals Q times delta V. I'm sure that you also remember conservation of energy. The question is, does a law of conservation of energy also apply to circuits? So let's do a little algebra to help us answer this question. If we rearrange our formula, we can now solve for the potential difference as a function of the potential energy divided by the charge that is moving through the circuit. For a given amount of charge, we can then think of conservation of energy simply as conservation of electric potential. Let's see how this applies in a circuit. According to Kirchhoff's loop rule, the sum of potential differences across all circuit elements in a single closed loop must equal 0. In equation form, it just simply is represented by the sum of the potential drops equals the sum of the potential gains. The circuit to the right, you can see, is just a simple parallel circuit with one battery and 2 resistors. In order for us to apply Kirchhoff's loop rule, we must identify the loops that we want to analyze. In this circuit, there are actually 3 loops. One, represented by the big green circle, and then 2 smaller ones, the orangish one, and then the blue one. So with that knowledge, we can now move forward. So let's look at an example. Using the circuit presented to the right, what are the magnitudes of the potential drops for V3 and V5 if the battery potential is 12 volts? Before we begin, can you predict which one, V3 or V5, will have the bigger potential drop? That may be difficult just by looking at the circuit to answer that question. But if we use Kirchhoff's loop rule, we can answer that question very easily. So how do we do that? Let's look at the red loop first. In this red loop, you can see we have the battery and 3 resistors. And 2 of the 3 resistors are the voltage drops are actually given. And our job is to then figure out the voltage drop in V5. So according to the loop rule, the voltage gained by V sub S is then going to be lost in V1, V2, and V5, which will then ultimately equal 0 volts as a potential gain and potential loss. So if we substitute in the given information, 12 volts minus 3 volts minus 5 volts minus V sub 5 is then equal to 0. And then with some simple addition and subtraction, we can find that V sub 5 is actually equal to 4 volts. How do we find V sub 3? Well, for V sub 3, we're going to use the blue loop. In the blue loop, again, you're going to notice that we have the source voltage, and then 3, in this case, 3 voltages that we now know, and 1 that we have to determine, which is V sub 3. Again, applying the loop rule, we have V sub S, and then we're going to subtract all the potential losses from that potential gain, and these will then equal 0 volts. So 12 minus 3 minus V sub 3 minus 3 again minus 4 is then equal to 0 volts. V sub 3 then comes out to be 2 volts. So you can see how Kirchhoff's loop rule makes analyzing circuits a lot easier. So let's practice. In this circuit, you will notice that there are actually 3 resistors, but now there are 2 batteries. So this seems a little bit more complicated. But we can still use Kirchhoff's loop rule to come up with an equation that we could then substitute numbers into to find whatever information we were asked to solve for. Another thing to note is that we have 2 currents, I1 and I2, given in the circuit. And that has everything to do with the fact that there are 2 batteries. With 2 batteries, I don't know how much the current's going to be in any given branch, so we just label them separately as I1 and I2. So let's go ahead and analyze this circuit. Starting at A, we're going to move clockwise to position B. Since there are no circuit elements, there's nothing for us to do at this time. As we move from B down to C, we're going to encounter resistor R2. When we encounter resistor R2, we know that there will be potential loss because of the equation V equals IR, otherwise known as Ohm's law. But as we move through R2, you'll notice that I2 is moving in the opposite direction as given by the diagram. When this occurs, this actually is going to mean that in our Kirchhoff's loop rule, that we're going to gain electric potential. So when we move through a resistor in the opposite direction in which the current is moving, we call that a potential gain. So we're going to write down plus I2 times R2, simply using Ohm's law within our Kirchhoff's loop rule equation. As we move from R2 to V2, we notice that we are moving from the positive side of the battery to the negative side. When this happens, that's going to be a potential loss. So remember, when we move from the positive to the negative of a battery, we're going to lose electric potential, not gain. So we're going to write minus V2. As we continue through the circuit from C to D, again, we do not encounter any circuit elements, so there are no parts of the loop rule that we need to worry about. Continuing up from A to D, we now encounter a battery V1, and in this instance, we're going to go from the negative side to the positive side. As a result, we're going to gain electric potential. So we're going to write plus V1. And then finally, we encounter R1. When we encounter R1, we are going through R1 in the same direction that the current I1 is moving as well. So this is going to represent a potential loss, and we will write a negative I1 times R1. To finalize the equation using Kirchhoff's loop rule, we would then have plus I2 R2 minus V2 plus V1 minus I1 times R1 is equal to 0. So what should we take away? Kirchhoff's loop rule simply states the sum of potential differences across all circuit elements in a single closed loop must equal 0. Kirchhoff's loop rule is a consequence of the conservation of energy. And finally, a general equation for Kirchhoff's loop rule is given below. Thank you very much. Hello, and welcome to this AP Physics 2 daily video on topic 11.6, Kirchhoff's loop rule. This is daily video number 2, and in this video we will discuss Kirchhoff's loop rule and how it can be represented by a graph of electric potential as a function of position within the loop. My name is Mike Fesco, and I'm an AP Physics teacher at Milton Godwin High School in Henrico, Virginia. Let's review. Kirchhoff's loop rule states that the sum of potential differences across all circuit elements in a single closed loop must equal 0. Kirchhoff's loop rule is a consequence of the conservation of energy, and the general equation for Kirchhoff's loop rule is given below. But let's now look at a slightly different way to represent the loop rule. Let's look at an example. According to Kirchhoff's loop rule, the total loss of electric potential as the current passes through a circuit is equal to the total gain in electric potential. As depicted in the diagram below, current traveling in the circuit from A to H and back to A passes through 3 identical light bulbs and a battery. The battery provides an increase in electric potential for the current, and each light bulb results in a loss of electric potential for the current. I wonder what a graph of this might actually look like. A graph of electric potential versus location in the circuit can provide a visual representation of the electric potential of current as it moves through the circuit. Starting at A, the current gains electric potential from the battery and is now at B. From B to C, the current moves through an ideal wire and there is no change in electric potential. As the current moves from C to D, it encounters a light bulb. The light bulb will remove a certain amount of potential from the current, and we call this a voltage drop. Because the light bulbs are the same, each will remove the same amount of electric potential. The current now moves from D to E with no change in potential, and we have the horizontal line on the graph. But from E to F, we encounter another light bulb, so we're going to lose electric potential again. And so as we go from E to F, there's going to be a drop on our graph. From F to G with another ideal wire, so no change in electric potential will occur in this section. And then as we move from G to H, we encounter another light bulb, and a voltage drop will occur again. Following Kirchhoff's loop rule, notice how the voltage gained is actually equal to the sum of all those voltage drops. So what would a graph of this circuit look like? In this situation, the batteries are not identical. So now we have 2 batteries, and we have 2 light bulbs. But we can still apply Kirchhoff's loop rule to this situation. So in this case, you will notice that from A to B, again, we have a large potential drop gain. Moving from B to C, we have ideal wire, so again, there will be no potential drop or gain. Moving from C to D, we move across a light bulb, so there'll be a certain amount of electric potential lost in that instance. Moving from D to E, ideal wire, no potential loss or gain. Moving from E to F, we encounter the battery. Please take note of how this battery is oriented. You will see that we encounter the positive side first and then the negative side. This means that we're actually going to lose potential as we go across this battery. And so as we go from E to F, we're going to see a potential drop. When we go from F to G, again, ideal wires, there will be no change in electric potential. And then from G to H, a light bulb is encountered, and we will lose electric potential again and return back to the battery at A. So for a battery, the sign of potential difference will be negative if you are moving from the positive terminal toward the negative terminal. So let's practice. Draw a series circuit that matches the graph to the right. The current through the circuit is 2 amps. You have 2 batteries. One, V1 is 10 volts, and the second, V2 is 4 volts. You also have 2 resistors. R1 is equal to 5 ohms, and R2 is equal to 2 ohms. In this situation, you are given the graph, and your job is to figure out how do I use those circuit elements to create that graph in a series circuit. So let's start at position A. If you note, according to the graph, as we go from A to B, it is a potential gain. So it would seem to make sense that we're going to use one of our batteries in this case, whether it's V1 or V2. Since the potential gain from A to B is much larger than any other potential gain in the graph, we're going to assume that from A to B that we're going to put V1, which is 10 volts. As we go from D to C, it's an ideal wire, so there'll be no change in our electric potential. We arrive at position C, and we note on the graph that there is a potential drop. Again, we're going to assume in this case, since we only have the two resistors, that the potential drops are going to be provided due to the current passing through either R1 or R2. Looking at our graph, we're going to see that there are two potential drops, one that is bigger than the other. So in this case, the smaller drop is what we encounter from C to D. So we're going to say that from C to D, R2, the 2 ohm resistor, would make the most sense. We move from D to E, which is an ideal wire again, so there's no change in our electric potential, and we now arrive at position E. At position E, we have a potential gain again. Well, since we just used V1 from A to B, it seems to make sense that from E to F, we're going to use V2 to provide our potential gain. As we move from F to G, again, we have an ideal wire, and so there's no change in our electric potential. And finally, as we move from G to H, we have a potential drop, and that potential drop is going to be caused by the current moving through resistor R1, and then return back to position A through an ideal wire. So we can see that Kirchhoff's loop rule works very well in helping us go from a circuit to a graph, and from a graph to a circuit. So what should we take away? The purpose of the graph is to visually display a variable as it changes with respect to another variable. An electric potential graph is a great way to show the changes in electric potential described by Kirchhoff's loop rule. The graph shows the increase and decrease in potential around the circuit, and the graph also shows that the total change in electric potential is always equal to 0. Thank you very much.
This is topic 11.7, daily video 1. In this video, we'll demonstrate the fundamental idea of Kirchhoff's junction rule by demonstrating similar ideas using easy to visualize objects, and then we'll apply it to a circuit. Hi, my name is Randall Stafford, and I teach physics at Rome High in Rome, Georgia, home of the award-winning Sound of the Seven Hills Band. So let's look at a physical example of what we will come to understand as Kirchhoff's junction rule. Well, what is this contraption? This contraption has nothing to do with Kirchhoff's law, but it's going to help us understand the breakthrough that the physicist Gustav Kirchhoff had in the mid-1800s. I'm a gardener. I have some property, and I always plant a big garden, and I'm always too busy to keep track of watering. So a couple years ago, I automated the process. I have a gizmo like this, which I don't know if you can see the end of it, but it's got this little fan in there, and as water flows down this tube, my garden keeps track of how much I've watered it. It keeps track of how much rain has happened. It's a really cool deal. My wife has called me a nerd. Okay, she's not wrong. But I grabbed a handful of these, and I'm going to use them to show you something that I think you'll find terribly obvious, and we're going to take that terribly obvious thing and apply it to Kirchhoff's rules. So this contraption here, I have a hose that's running, this is on a lab table in my classroom. I have a hose that is running water into here. It's not turned on right now. But as soon as I do, it's going to start spinning this little blade in this pickup. And the amount of water in milliliters that has flowed through here is going to be reported on this display. Fancy Arduino electronic stuff. If you're not into it, it makes for a great hobby. And then the water that flows through this monitor is going to split up. And some of it's going to go this way, and some of it's going to go this way. As a matter of fact, I'm going to kind of semi-close this one so that more water will flow through this one than that one. So let me turn it on, and we'll watch how these dials change. But I will tell you this much. In a perfect world, the amount of volume of water that goes through this unit will equal to the amount of water that goes through this plus this. I will say that this is not the intended use for these, so we're going to be maybe within 20% or so. But let's give it a try. I'm turning on the water. And you can see we've started reading here. There was some air in the line, so that's going to throw us off a little bit. But you can see that all three are reporting the volume of water that has gone through these pipes. This one, well, we've just broken 1,000 milliliters, so that's a liter has gone through this one. But we're right at 1,000 now, total between those two. The reason they don't completely add is we have this volume of water here that's going through. So the more I let this run, the more you'll see that this number roughly totals the sum of these two numbers. So what's the takeaway? Well, think about what I'm doing here. I'm saying I'm running a bunch of water into an intersection. I'm splitting the water up unevenly, as a matter of fact, more going through this part than this part. But the amount of water that goes into this little T intersection should equal the amount of water that comes out of this T intersection. That is all that Gustav Kirchhoff's junction rule is. He didn't say about water, but he said about current, about electric current, specifically about electrons. He says that the electrons that go into an intersection is equal to the electrons that come out of the intersection, or actually he said it using current. He said the electric current going into an intersection is equal to the sum of the electric currents coming out of the intersection. And I use this as a demonstration to kind of get our head around it to show you how completely obvious it is. When we do it this way, the reason that the output, the sum of the output is equal to the input is that the mass of this water is conserved. The reason it works in electric circuits is because the charge is conserved. We call the flow of water current. We call the flow of electricity current. Both of those things, we use the same word because they're nearly identical. So that, in a nutshell, is Kirchhoff's junction rule. So we can apply that idea to actual current in a circuit. I built this crazy contraption here. Let me show you what the circuit looks like. It's pretty simple. It is a battery that goes into a resistor. This arrow here means it's a variable resistor. I'll show it to you in the circuit itself in a moment. We then have an ammeter hooked up that is the yellow wires. It then branches into a parallel part where we also have some resistors that are variable. And I have two amp meters hooked up there, one with green wires, one with blue wires, and then they join back together and come back and go into the battery. So according to Kirchhoff's junction rule, the current through the yellow amp meter should equal the current through the green plus the current through the blue. Let's look at the actual circuit. It is right here. These are the variable resistors. It's just a volume knob. And right now I don't have a battery hooked up, so no current is flowing. So as soon as I hook up this battery, what we should see is the current flowing through the yellow amp meter is equal to the current flowing through the blue one plus the green one. So let me reach across here and hook it up. Oops, there we go. Yes, that's very good. I will say that I buy the rather inexpensive multimeters for my classroom, so these are going to be pretty close. Right here we have the current going through the yellow resistor as 1.16, that's milliamps. And here we have 0.47 and 0.68. Adding those together, that's 1.15. Oh, looky there. Now let me change one of these variables. So because these are variable resistors, I can increase or decrease them. These resistors will swing between roughly 10,000 volts and pretty close to 0. So I've just kind of dialed all three of them. Now I have, let's see, 36 and 78 is 114, 1.14 amps is the total here. And here it reads 1.1314. Well, it could make up its mind. And again, I buy these meters for less than $10, so they're guaranteed to work. Fairly close. We've now changed it to 1.12, and we're at 1.13. Yes, this is Kirchhoff's junction rule. It is a great tool for helping us analyze circuits. So algebraically, we can state Kirchhoff's junction rule as the sum of the currents into the junction is equal to the sum of the currents coming out of the junction. It's a very straightforward idea. Why don't we look at an example and see if we can apply it to some circuit analysis. In this circuit, the current through the battery is 15 amps. Which of the following correctly describes the currents into and out of point A? Well, let's see. We're told that we have 15 amps coming out of the battery. All of that goes through resistor 1, which means 15 amps is going into point A. Well, already we can eliminate choice A from the multiple choice, because it tries to imply that only 5 amps are going into that intersection, and we know that's not true. So the answer must be B, C, or D. Well, current 1 goes into the intersection, and coming out is current 2, goes through resistor 2, and then a current that we're going to call current 3, 4, because that current divides again, and some of it goes through resistor 3, some of it goes through resistor 4. So we have to look at what happens at point B. Well, Kirchhoff's junction rule works at point B also. Current going into it is what we've labeled I sub 3, 4. Coming out of it is current 3 and current 4. Well, you'll notice that R2, R3, and R4 are all in parallel with each other, which means the voltage drop across them is the same. But since resistor 2 is smaller than 3 or 4, it's going to get the bulk of the current. And we know that resistor 3 and resistor 4 are going to evenly divide their current. Well, from that, we can eliminate all of the answers except for C. We have 15 amps going into the circuit, into the intersection at point A. 7.5 amps is coming out through resistor 2. Resistor 3 and 4 each have 3.75 amps. If you'd like to verify that, you can do Kirchhoff's loop and junction rules to completely analyze that circuit. That was a great little problem. So what can we take away from our analysis of Kirchhoff's junction rule? His junction rule is a consequence of conservation of electric charge, and the total amount of charge entering the junction per unit time must equal the total amount of charge exiting the junction per unit time. And finally, the relevant equation is the current in to a junction is equal to the current out. Hope all that benefited you, and I appreciate you watching the video. Thank you. This is topic 11.7, daily video 2. In this video, we'll work through a sample question using Kirchhoff's junction rule in our analysis. My name is Randall Stafford. I teach physics at Rome High in Rome, Georgia. Go Wolves. So I've got a free response question from some number of years ago that I want to work through with you. I'm going to do it on my dot camera, and I want you to work it as we go along. So stand by while I switch to my dot camera. So here's the problem. The circuit shown contains a battery with negligible internal resistance, a closed switch S, 3 resistors, one of the resistors of resistance R, and 2 with resistance 2R. So a resistor C has a resistance of R, resistance A and B each have a resistance of 2R, and we are asked to rank the currents in the 3 resistors from greatest to least, with number 1 being the greatest. If 2 resistors have the same current, give them the same ranking, and it asks us to justify our answers. So according to Kirchhoff's junction rule, we are going to look at this intersection right here. We have current going into the intersection. We're going to call that IA. It's coming out of the battery going through resistor A and into that intersection. And then we have current coming out. We'll call that current B, and current coming out this way. We'll call that current C. And according to Kirchhoff, let's do it here. IA is equal to IB plus IC. Well, clearly IA is the largest. If these two have to be added up together to get IA, then IA must be the largest current. We can also say that all of the current is going through resistor A, and all is greater than any part. So yeah, so the highest current is current through resistor A. Now, the current split here, one going through B and one going through C, which one of those, if either, is greater? Well, using Ohm's law, change in voltage is equal to IR. Well, since resistor B and C are in parallel with each other, then the voltage drop across them must be the same. So voltmeter here. Whatever this reading is, looked up in parallel in both cases, whatever this reading is, it's going to be the same, which means the change in voltage is the same for both B and C. However, since resistor B has a greater resistance, that means it must have less current. And therefore, resistor B must be in last place, which puts resistor C in middle place. So resistor C is 2, and resistor B is 3. So here in part B, we're asked to rank the voltages across the 3 resistors from greatest to least, and if anything's a tie, then use the same ranking for it. Well, we still have what we got a moment ago, Kirchhoff's junction rule. Oops, let's draw my arrow, where IA is equal to IB plus IC. Well, as I said a little bit ago, the voltage across these two have to be the same. So whatever's true, resistor B and resistor C are going to tie. So let's think about resistor A, whether it's greater than or less than these. Well, so you'll notice that the resistance is the same in resistor A and resistor B. So if we look at Ohm's law, change in voltage is I times R. Since both resistors are the same, 2R and 2R, the one with the greatest current must have the greatest change in voltage. Well, and since a moment ago in part A, we decided that current A was biggest, that must mean the voltage drop across resistor A must be biggest. So that puts it in first place. And in the tie for second place, with what we said a moment ago about them being in parallel, is voltage drop across B, tied with voltage drop across C. Let's look at the next section. Here, we're told that for parts C through E, use a voltage of a battery of 12 volts, and R is equal to 200 ohms, which means this is equal to 200. RA is equal to 400, and RB is also equal to 400. Well, for part C, we're asked to calculate the equivalent resistance of the circuit. Well, the rules for that, we look for any resistor that is in series with the next door neighbor. I don't see any, so I move on to step 2. Look for any resistors that are in parallel with the next door neighbor. I do see a couple, B and C. So 1 over R equivalent, let's call it EC, is equal to 1 over resistance B plus 1 over resistance C. So that would be 1 over 400 plus 1 over 200 ohms. So the equivalent resistance across BC is, I'll leave you to your calculator to do that, but it comes out to 133 ohms. But that's only part of the story. We've replaced B and C with their equivalent, but now we have to replace A with its equivalent. So now we have a 400 ohm in series with 133 ohm. So the equivalent resistance for the entire circuit would be RA plus RBC. So that would be 400 ohms plus 130 ohms. The equivalent resistance for the entire circuit is 533 Oops, I was a little messy there. Sorry about that. It's a beautiful thing. Okay, calculate the current in resistor C. Well, why don't we use Kirchhoff's loop rule for that? Before we do that, we're going to need to know the total current in the circuit. Well, that's pretty easy. The reason we simplify our circuit is so that we can apply Ohm's law. Change in voltage is 12 volts, is equal to the current that we don't know times the equivalent resistance that we do know. When we throw that in our calculators, we find out that the total current in the circuit is 0.0225 amps. So now let's use the loop rule, Kirchhoff's loop rule. The sum of the voltages minus the sum of the IRs is equal to 0. Well, we're just looking for the current through C, so why don't we choose a loop that looks like this? It's just this outer part right here. Okay, we should be able to do that. Let's see. The only battery voltage source we have is the battery, 12 volts, minus, well, I have current through here, so it would be the total current, 0.0225 times the resistance of A, 400, minus this current, which I don't know, but I want to know, times this resistance, 200, and all of that, ran out of room, is equal to 0. Well, if I throw that in my calculator, I want to find out that the current going through C is 0.015 amps. Oh, it's a beautiful thing. And now the last part, C. The switch is open, resistor RB is removed and replaced by a capacitor of capacitance 2 microfarads. The switch is again closed. Calculate the charge on the capacitor after all currents have reached their final steady state values. Well, when we first close the switch, all of the current is flowing through this part of the loop. None of it's going here because this capacitor has no charge on it. But over the course of time, charge builds up on the plates, and less current flows through the smaller portion, flows through the capacitor, and more flows through this other resistor out here. So after a long period of time, all of the current is going around this part of the circuit. So let's figure out how much current that is. Well, equivalent voltage equals IR. 12 is equal to, I don't know what the current is, but the resistance, I have a 400 ohm and a 200 ohm in series. That would make for 600 ohms. That makes, after a long period of time, the current in the circuit 0.02 amps. Okay, so now, if we want, we can use Kirchhoff's loop rule for this inner part here. Let me do that. Just for this smaller loop, I'm going to say sum of the voltage minus the sum of the IRs is equal to 0. When we have 12 minus, here we're going to have a current of 0.02 and a resistance of 400 ohms, minus here, well, we don't have any current flowing. There's no IR, but there is a voltage drop. And you'll recall from the equation sheet, that equation determines the voltage drop across the capacitor. We're going to cross multiply that. We're going to put it right here. So the charge, Q, that's what we're looking for, over the capacitance, 2 times 10 to the minus 6, is the voltage drop. So that's the sum of the voltage drops, and they're equal to 0. If you throw all that into your calculator and solve for charge, you're going to find that it is 8 times 10 to the minus 6 coulombs. Ah, I love it. It's a beautiful thing. So what are our takeaways? Well, first off, Kirchhoff's junction rule is a very useful tool in understanding how circuits function. And when you couple the junction rule with his loop rule, it allows for some very detailed algebraic analysis of circuit functionality, and that's a beautiful thing. Thank you for your time. I hope you enjoyed this video, and I hope it was helpful. This is topic 11.8, daily video 1. In this video, we will explain the behavior of capacitors when they are arranged in series inside a circuit. My name is Randall Stafford. I teach at Rome High School in beautiful, scenic Rome, Georgia. And we are going to take some capacitors, right like that, and we are going to put them in a circuit in series. We're going to see how they behave. So to start with, I'd like you to look at the equation sheet. There's actually 2 equations that govern how capacitors work. It is these 2 right here. You don't have any control over the variables in the second equation. Somewhere in some factory where they made the capacitor that you're going to use, they decided how big the area of the plates were going to be. They decided how far they were going to separate the 2 plates from each other, and they decided what material was going to go between the 2 plates to separate them. That's this kappa right here, the dielectric constant. So all of those variables were set long before you ever got your capacitor. Once you put your capacitor in a circuit, this is the equation that is in view, and we're going to examine that, and we're going to see that that tells us everything we need to know about how this capacitors behave once they're in series in a circuit. So let's go to a simulation. This is a FET simulation, and as I said just a moment ago, when they were manufacturing capacitors, they decided how much area. Let me turn on the capacitance. They decided how big the area of the plates were going to be, and that fitted with the value of the capacitance, how much they were going to be separated by, and they decided what material to put between the plates. All of that decided the capacitance. All well and good. That's not what we're worried about today. We're worried about putting them actually in a circuit. So here's a circuit with one capacitor, and yes, I can adjust it here, and that does adjust the capacitance. We're going to pick a nice even number. We're going to pick 2 times 10 to the minus 13 farads. And if we apply some voltage, some charge appears on both plates, positive charge on the top plate, negative charge on the bottom plate. And so we've stored some charge in our capacitor. Well, how much? That equation that we got off the equation sheet is going to tell us everything we need to know. We also, while we're here, we should measure the voltage drop. Now, we'll put these probes here, but I imagine you can figure out what the voltage drop is without any help from me, because the only thing in the circuit is that capacitor. If the voltage of the battery is 1.5 volts, then the voltage drop across the capacitor has to be 1.5 volts. Okay, now let's switch to our document camera, and we'll work through a little bit of math. So the equation we got off the equation sheet was capacitance is equal to charge over change in voltage. We're going to cross multiply that. We're going to say that charge stored in our capacitor is the capacitance of the capacitor times the change in voltage. Okay, we're good to go. You'll recall that the capacitance was 2 times 10 to the minus 13 farads, and the change in voltage was unsurprisingly 1.5 volts. Oh, the good news is we can do that math in our head. 2 times 1.5, so 3.0 times 10 to the minus 13 coulombs. I like to write out the unit just so it doesn't get confusing with this capacitor here. So that's the amount of capacitance we have stored in our capacitor. Okay, all well and good. Now let's switch and get in our two capacitors in our circuit. So we get these probes out of the way here. I'll turn this capacitance off just for a minute. So now we're going to have two capacitors in series. This first one is 2 times 10 to the minus 13 farads, and we'll make this other one, say, 3 times 10 to the minus 13 farads. So my question for you is, how much charge is stored total in those two capacitors? Is it more than when we had one? Is it less, or is it the same amount? I'm going to find out by putting this probe right here, figure out what the voltage drop is across the first capacitor. A moment ago, it was 1.5 volts, but obviously if you think about it, it's going to be something less than 1.5. The voltage drop here now is 0.9 volts, and on the other capacitor, the voltage drop, we'll probably use your golf school to figure this out, is 0.6. So the voltage drop across each capacitor is different, which means the amount of charge stored in that capacitor is different. So let's do just a bit more math. So let's see, now we have the charge stored in capacitor number 1 is capacitance number 1 times the change in voltage 1. Well, let's see, that is still 2 times 10 to the minus 13. The drop in voltage was 0.9. Oh, and I can do that math in my head. That is 1.8 times 10 to the minus 13 coulombs. So you'll notice that less charge is stored in the capacitor now that it's in series with another one. Let's look at the other one, Q2, capacitance 2, change in voltage 2. So this was a 3 times 10 to the minus 13 farad capacitor, and the voltage drop there was 0.6 volts. And that math, 1.8 times 10 to the minus 13 coulombs. So it is worthy of noting that in both cases, the amount of charge stored in the capacitors is the same. If you think about it, that's really what had to happen. I want you to examine this lower plate of the first capacitor, the wire, and the upper plate of the second capacitor. Those three components are all conductors, and they're connected together. And right now, there is no net charge on them. If we put a little voltage there, well, no electrons jump to the other plates. What really happens is you get a little polarity here. The electrons that are on the bottom plate migrate to the top plate. So the net charge on the middle component, wire plate, is 0. That means I have 1.8 times 10 to the minus 13 coulombs worth of charge on the top plate, the exact same magnitude, opposite sign, on the bottom plate, same on the top plate, same on the bottom plate. So the total charge stored in the two capacitors is less than when we had one capacitor. So since the charge on both capacitors is the same, here's what we can say with a high degree of confidence. The total voltage in the circuit is equal to the change in voltage across capacitor 1 plus the change in voltage across capacitor 2. Well, but we can also express that as the charge stored in 1 divided by the capacitance of capacitor 1 plus the charge stored in 2 divided by the capacitance of capacitor 2. But just a moment ago, we decided that these charges, Q1 and Q2, are the same. So I'm just going to write that again and call it V total is equal to Q total over C1 plus Q total over C2. And then since those are the same values, I can factor them out. And as a matter of fact, I can factor them out and divide both sides by them. So I end up with this beautiful piece of mathematics. V total over charge total is equal to 1 over C1 plus 1 over C2. And this is really just the equivalent capacitance of the entire circuit. So we're going to write that as 1 over C equivalent is equal to 1 over C1 plus 1 over C2. The way you add capacitors when they're in your circuit in series is this math. It's interesting to note that the way you add capacitors in series looks very much mathematically like the way you add resistors in parallel. But also you can realize that whatever the value of your smallest capacitor is, the equivalent capacitance is going to be less than that. So that's how you add capacitors up in series in your circuit. So what should we take away from all this? Well, when capacitors are connected in series, the equivalent capacitance is calculated using this formula. 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus however many capacitors you have wired up in series. And the equivalent capacitance of a set of capacitors in series is less than the capacitance of the smallest capacitor. Hope that was helpful. Thank you. This is topic 11.8, daily video 2. In this video, we'll examine the behavior of capacitors when they are arranged in parallel in a circuit. My name is Randall Stafford. I teach at Rome High School in beautiful, scenic Rome, Georgia. We're going to do the same thing we did in the previous video, except now we're going to wire up a couple of capacitors in parallel, not in series. Here we have our capacitor in series. When I switch them to parallel, you'll notice I have a 2 times 10 to the minus 13 and a 3 times 10 to the minus 13. When they're in parallel, we have the exact same thing, 2 and 3 times 10 to the minus 13. But recall from the previous video that when we added the second capacitor in series, the voltage drop across the capacitor diminished. When there was just one capacitor here, the voltage drop was the entire voltage drop of the battery, in this case 1.5. When we add a second one, the voltage drop is now less than the voltage drop of the battery. Okay, all well and good. What about when they're in parallel? Well, one of the things about a parallel circuit is that the voltage drop across the objects in parallel with each other is the same. So here we can say that let me put a low voltage on here. The voltage drop across capacitor 1 is still 1.5 volts, and the voltage drop across capacitor 2 is still 1.5 volts. And that is exactly the opposite of what it did when we wired them in series. What that means is that we now, when they're wired in parallel, we now have the ability to store much more charge than we could when we only had the one capacitor. So let's look at a little bit of math. The equation that we're focused on, straight off the equation sheet, capacitance is charge stored in the capacitor divided by change in voltage. But in this case, we noticed that when they're wired in parallel, that the amount of charge actually increased. We can say that the total charge stored in the circuit is the charge stored in capacitor 1 plus the charge stored in capacitor 2. Well, we can express this. We cross multiply this. We get Q is equal to C times delta V. So that means the total charge is equal to capacitor 1 times change in voltage 1, which again in our simulation, that was 1.5 volts, plus capacitor 2 times the change in voltage of capacitor 2, which was also 1.5. So we don't have to use the subscripts V1 and V2. We can say that the total charge is equal to C1 times delta V total plus C2 times delta V total. And then we can factor delta V total out and divide both sides by it. So we'll have Q total over change in voltage total is equal to capacitor 1 plus capacitor 2. But this is nothing more than this. So that means that we can express this as the total capacitance. We usually write that as equivalent capacitance is equal to C1 plus C2. So in a extremely straightforward way, we get that the capacitance of a couple of capacitors wired up in parallel just add algebraically. The equivalent capacitance is C1 plus C2. But we also get the fact that when you add up these capacitors, the equivalent capacitor will be bigger than whatever the largest value is here. So with capacitors in series, the equivalent capacitance is smaller than the smallest. With capacitors in parallel, the equivalent capacitance is larger than the largest. Let's switch back to the equation sheet just for a moment. So if you look down here, we have the equation for capacitors in series and for capacitors in parallel. And you can realize that those are similar and yet different to resistors. That is, the math is exactly the opposite. We can tie all this together by looking at this. The equation that governs resistance is this one. These are the variables set in the factory. And notice what happens to area in these two equations. In capacitors, the area is in the numerator. For resistors, the area is in the denominator. If you think about what happens when you put two capacitors in parallel who are increasing the area, it's like I have one big capacitor with one very large metal plate up here and an identically sized metal plate down there. When you put resistors in parallel, you also increase the area, the cross-sectional area of the resistor. So since area is in the numerator for capacitors and the denominator for resistors, that gives us quite naturally the fact that these two pieces of math would be the opposite of each other. So what should we take away from all this? Well, when you have capacitors connected in parallel in a circuit, the equivalent capacitance is calculated using this formula. C equivalent is equal to C1 plus C2 plus however other many capacitors you put in parallel. And the equivalent capacitance of a set of capacitors in parallel is larger than the capacitance of the largest capacitor. Hope that was beneficial to you. Thank you. Topic 11.8, Daily Video 3. In this video, we will examine the behavior of RC circuits with various time constants. My name is Randall Stafford. I teach physics at Rome High in idyllic Rome, Georgia. Let's build us a simple circuit to start with. It's going to be really simple. It'll have a battery, a resistor, a capacitor, and one switch. And we're going to want to observe what happens to the capacitor and the current as we close the switch and as some time goes by. So to do that, we're going to need to hook up a voltmeter. Remember, you always put your voltmeter in parallel with whatever it is you're trying to measure. Voltage across two things in parallel are the same. So if you put your voltmeter like this, you'll actually measure the voltage across the capacitor. Put a voltmeter in series, and you get no usable information. We're also going to want to track the current. So we're going to hook up an ammeter, and an ammeter is always hooked up in series. If we put it in parallel, some of the current would go through it, and some would go through the other branch of the parallel part of the circuit. We wouldn't get any good results. So always remember, voltmeters in parallel, ammeters in series. Okay, so we're going to close the switch, and the very first thing that's going to happen is some current is going to start to flow through our circuit. At the very beginning, that capacitor has no charge on it, and so it's going to act like just a little piece of wire was connecting those where the capacitor is, and so there'll be great flow of current. However, as time goes by, charges will start to assemble on both plates, positive on one side, negative on the other, and as that happens, it builds up an electric field, and the current finally fades away to zero. And by this point, after some long period of time, the capacitor has a full charge and there is no current flowing. So I say after a long period of time, let's see what that looks like. Well, the current will start off with some big number and will taper away and asymptotically approach a zero. That is an exponential decay curve. The voltage on the capacitor, well, when I first closed the switch, there was no voltage there, so it started off at zero. But over time, more and more charge built up on the capacitor, and the voltage across it grew exponentially and eventually asymptotically approached some voltage to be, in this case, the voltage of the battery. Now, as I said, that happens over some period of time. What if we built this circuit instead of using a resistor if we had used a light bulb? Well, from the equation sheet, power in a circuit is I times delta V, but you can rearrange the variables using Ohm's law and get that power is I squared times R. So whatever the resistance of the light bulb is, the brightness, the power, would be proportional to the square of the current. So when we first close the switch, the light bulb is going to be very, very bright, and it's going to taper away and get dimmer and dimmer and dimmer, and eventually it's going to drop out. Okay, well, all that's well and good. If we then opened up the switch, absolutely nothing would happen. I've reset the graphs. Nothing would happen. That capacitor will remain charged for a very long period of time. But if we were to connect a jumper wire, little red wire here, the moment we do, current starts to flow in the opposite direction. That is, the capacitor starts to discharge. And initially, there's a lot of current flowing, but over time, as the capacitor continues to discharge, that current fades away and eventually goes to zero. That's a very fancy animation. You got to like that. Well, so what happens with current? Well, just like it did before, it starts out gangbusters and it tapers away to zero, which means the brightness of the bulb, the moment you connected that red wire, the bulb would be very, very bright and then fade down to dim and eventually turn off. The charge on the capacitor, well, it started fully charged, and now we're discharging it, which means it would have an exponential decay. All of this happens over some period of time. What we really like to do is now kind of examine what I mean by some period of time. The RC time constant. The time constant of an RC circuit is a measure of how quickly the capacitor will charge or discharge, and is described by the equation. Let's see. That first letter is Greek letter tau. It looks like you were trying to draw a pi and just cut it in half. Tau, the time constant, is equal to the equivalent resistance times the equivalent capacitance. Well, that seems straightforward enough. So if I have a value for the time constant that is small, my capacitor charges with a curve that looks like that. If I have a time constant that is rather large, then the curve looks more like that. Those are both exponential growth curves, but just one takes much longer than the other. When you're charging a capacitor, the time constant represents the time required for the capacitor's charge to increase from 0 to approximately 63% of its final asymptotic value. And if you're like my students, when I say 63%, they immediately give me this funny look like, where did that random number come from? Well, hold on a minute, I'll try to make it make some sense. So if this is our capacitor charging, then when enough time has gone by to where it's equal to that tau, R times C, then it is risen to a value of 63% of its final asymptotic value. So what if you're discharging an already charged capacitor? Well, it takes some time also. For a discharging capacitor, the time constant represents the time required for the capacitor's charge to decrease from fully charged to approximately 37% of its initial value. So 63%, 37%, I know they seem random, but let me show you where those numbers come from. this is your discharging capacitor, and that is the 37% mark. Well, what I'm about to tell you is not strictly speaking part of physics 2. It's just actually just a smidge, about a centimeter past the end of physics 2, but it will help you understand these two percentages. This is the equation that governs the voltage drop across the capacitor as it's charging, and this is the equation that governs the voltage drop across the capacitor as it's discharging. So V naught in the circuit we have in question here, that would be the voltage of the battery, 1 minus exponent raised to the negative time over the time constant. So if you think about it, when little t is equal to tau, the time constant, then that's e raised to the negative 1. Well, if you grab your calculator, you will realize that e raised to the negative 1 is about 37%. So that's where those two percentages come from. Not nearly as random as it first seemed. But at least now we know that we can calculate how long it takes for a capacitor to charge or discharge based on the value of the equivalent resistance and capacitance in the circuit. So let's look at a slightly more complicated circuit. We have a circuit here. It's got two resistors and one capacitor. The capacitor and one of the resistors are wired in parallel. So the moment we close the switch, all of the current is flowing in the branch with the capacitor. Remember, when the switch is first closed, that capacitor acts like just a short in the wire, so none of the current would flow through the resistor. All it would flow through the branch with the capacitor. So we can calculate how much current is flowing in the circuit immediately after the switch is closed. The equivalent resistance in the circuit is 10 ohms. It's as if R2 wasn't even in our circuit since no current is flowing there. So using Ohm's law, we have 20 volts from our battery is equal to current times 10 ohms. The current flowing through the circuit is 2 amps. Okay, that is immediately after we close the switch. But after time, charge builds up on the capacitor, and less charge flows through that branch of the circuit, and eventually no current is flowing through that. So all the current is now going through R2. Well, now we have a different equivalent resistance in our circuit. After a long period of time, the equivalent resistance is 20 ohms, right? R1 plus R2 in series. Using Ohm's law, we find that 20 volts from the battery is equal to I times 20 ohms. The current has now dropped to 1 amp. So how would this have all behaved if this had been light bulbs instead of resistors? Well, the moment we close the switch, the light bulb number 1 would have been very, very bright, and it would have started to dim over time. As that was happening, R2 would have not been shining at all, and it would have gotten brighter and brighter and brighter, and eventually, when we got to steady state, both bulb 1 and bulb 2 would have the same amount of brightness. So what should we take away from all this? Well, the potential difference across the capacitor and the current in the branch of the circuit containing the capacitor both change over time as the capacitor charges or discharges, but both will eventually reach a steady state after some long period of time. Immediately after a potential difference is applied to an uncharged capacitor, charge can easily flow to or from the plates of the capacitor, and after a long period of time, a charging capacitor will become fully charged, reaching a maximum potential difference, which there is zero current in the circuit branch in which the capacitor is located. Hope that was helpful. Thank you very much. Topic 11.8, daily video 4. In this video, we will measure short-term and long-term potential difference across capacitors in current in RC circuits. This is Randall Stafford, and I teach physics at Rome High in Rome, Georgia. So we're going to actually physically build some circuits today. So let me switch my back to the camera and show you this stuff in action. So while we're here, why don't we recap everything? In the first couple of videos, we talked about capacitors that are wired in a circuit in series and in parallel. Let's take our big container of capacitors. I have one right here, and I'm going to pick, I'm going to pick a 100 microfarad capacitor, and let's say a 470 microfarad capacitor. Well, come on, there we go. Let's see, if we were to wire these in series, we'll call C1 100 micro and C2 470 micro. So in series, it'd be 1 over 100 microfarad plus 1 over 470 microfarad. You can check my math. I believe that works out to 82.5 microfarad. That's in series. And then if we put them in parallel, it would just be C1 plus C2, so 100 microfarad plus 470 microfarad. So that would be 570 microfarad. Well, let's test them. I have here a meter that is designed to measure a number of things, including capacitance. I have our two capacitors here. I'm going to wire them up first in series. When you build circuits for yourself, you may want to make them a little more permanent than this. But there, those are in series with each other. I'm going to take my meter. I'm going to hook up this lead to that end and this lead. As I said, you might want to make them a little more permanent than this. This one. And we've now come far enough on our journey to realize that it takes time to charge up capacitors. So I've got a little bit of current going through here, and it's charging up. And here in a couple of minutes, it should, a couple of seconds hopefully, should catch up. Yes, we were expecting 82.5 microfarads. It's about 81 microfarads. I do buy the kind of cheap capacitors. They're all within about 10%. So yeah, that's very good. Let's try it now, wiring them up in parallel. That actually turns out to be kind of easy, because all I have to do is join the ends. Give it a good twist. And we'll hook up one lead to this one, one lead to that one. Come here. That's going to charge these capacitors. And we're expecting something in the neighborhood of 570 microfarad. Right now it's registering nano. Switch to that. All right, 570. It came up to 593. That's well within the 10% we were expecting. Yes, it turns out our understanding of how capacitors work in series and in parallel is accurate. Now let's combine a capacitor with a resistor. I'm going to move all this stuff out of the way. So this circuit here, we're going to use to charge up a capacitor and see how the voltage changes as we both charge it and discharge it. And this circuit is built right here. This white thing is called a breadboard. And if you've never seen one before, it's a little confusing. All these little holes on the end pieces, the top two rows are connected horizontally. That is, all of these dots on the top row are connected to all the other ones. Same thing with the second row. We're going to use that as our positive and negative for a battery that we're going to hook up here in just a moment. But then, if you'll just follow the yellow wire, the positive charge is going to come out of the battery and go through the resistor. That'll be right here. We've got a 10,000 ohm resistor hooked up. We're going to come out of the resistor and go into the capacitor. Here's our capacitor right here. Through the capacitor, through a couple more wires, and then back to the negative side of the battery. What we're also going to do is we're going to hook up a voltmeter, kind of a fancy voltmeter. We're going to do it in parallel. Remember, your voltmeters are always in parallel. So we're going to hook them up there with a piece of software from the Vernier company. to this gizmo, which is broadcasting through Bluetooth however much voltage is on the capacitor to a piece of software that I have right here. This graph here, we have time on the horizontal axis and voltage on the vertical axis. So in a moment, when we fire all this up, we should see that exponential growth curve that we were expecting, that we derived in the last video. So I'm going to start with, I'm going to hook up a wire that will keep keep the capacitor from charging while I hook the battery up. So here's the positive lead. There's the negative lead. We're going to set our software to start collecting data, and then I'm going to remove this. Watch the graph. Look at that. Oh, it's beautiful. That exponential curve. Oh, it's a gorgeous thing. With a 10,000 ohm resistor and a 470 microfarad capacitor, the time constant, tau, is about 4.7 seconds. So in just a little less than 5 seconds, the capacitor went from a potential drop of 0 to a potential drop of somewhere close to 62% of its final asymptotic value. Now, I can also let it discharge, like we showed in the previous example. There. Now we have exponential decay. And if I disconnect that, we'll have exponential growth again. Now, if we wanted to, we could replace the capacitor or these resistors with different values of resistance. Let's do that for one of these. I have two spares here. One has a very, very short time constant. The other has a rather long one. Let me hook up the rather long one. So I've replaced our 10,000 ohm resistor with a 33,000 ohm resistor, and that will give a time constant of more like about 15 seconds. So we should see it rise much more slowly. Let me hook up power, remove my jumper wire. I'm going to collect some data. Okay, you can see that curve is much more shallow. It's still exponential, but it's going to take a much, much longer period of time to asymptotically approach 9 volts. The time constant for this one is 15.7 seconds. So hope that connects all those dots for you. Anytime you see a little LED flashing on and off, somewhere inside that gizmo is a capacitor charging and discharging just like this one is doing. So what are the takeaways from all this? Well, first thing, the potential difference across the capacitor and the current in the branch of the circuit containing the capacitor both change over time, as we saw, as the capacitor charges or discharges, but both will reach a steady state after a long time interval. And immediately after a potential difference is applied to an uncharged capacitor, charge will flow easily to and from the place of the capacitor, but after a long period of time, a charging capacitor approaches a state of being fully charged, reaching a maximum potential difference at which there is zero current in the circuit branch in which the capacitor is located. Hope that was beneficial to you. Thank you.